Welcome to SkyTour LiveStream.
Hello, folks. Sorry, it's a night of Universe Sandbox tonight. The sky is not conducive to the starry skies, although I have good news about all that. Keith is here with me. Hey, Keith, what's going on?
Hello.
Exactly.
We decided to do a stream tonight, guys, because we didn't get to do one over the weekend where I usually have Mark on P&K, so we decided to crash some planets together and, the shenanigans we get into.
Exactly, the shenanigans. Now, I mean, besides the shenanigans, we're going to be doing some other really cool things. Like, for instance, this view we're looking at right here. This is Oumuamua coming into our solar system. It's right there. All right, and Oumuamua is going to go around our sun. If you remember, back in 2017, Oumuamua came zipping in October, and it moved so fast, literally 190,000 miles an hour. Or roughly 83 kilometers per second, came in so fast. And on SkyTour Radio last week, we actually talked about what would happen if Oumuamua struck our planet. Hey, Keith, we might be able to arrange that. Maybe figure out a way to throw an asteroid about the size of Oumuamua into the planet to watch what happens. That might be cool. So I think.
Yeah, let's murder everybody.
Well, and we are paused. What's that?
Chat says Keith is a little quieter than you. That might be because I wasn't really talking all that much, but
well, you could just raise your levels.
I can up the levels a little bit if you want me to.
Yeah, I'll raise my levels too a little bit. See, so now I'm even higher than you.
Oh, there we go. So
good.
Hopefully that'll work out for you.
Awesome.
I don't think I'm still at 0 decibel. Yeah, I'm good.
Very good. Very good. Very good.
I got to turn my headphones down because I'm deafening. Yep. So.
I want to say hi to Alfred Grimmett is here. Zarix is here, and Deb Mahern. Hello. Hi guys, welcome to SkyTour LiveStream, and we are also simul-streaming over on P&K Space Imaging. So is in our chat, and in P&K's chat, we're all one big happy family today as we murder the solar system in Universe Sandbox 2.
Mark is paying attention to the SkyTour LiveStream chat, and I'm paying attention to the P&K chat. So, just work with us.
Yeah.
We'll try to see everybody.
Well, you could just
a little quiet. What the heck? Okay.
We could each bring up our own chats. Each other's chat too.
Yeah, that's true.
We could really make it complex. I mean, to me, that's not very complex considering, how many things I run when I do a normal SkyTour live stream.
Yeah.
We got lots of things going on.
Yeah. We'll wait till this baby starts crunching some numbers.
Oh yeah, this is gonna this is gonna go fast. And the thing is, I did something with Universe Sandbox 2, which is kind of fun. I actually created a star by throwing all kinds of gas, and you can throw gas, literal gas clumps, into a center of a cloud and make a cloud, and it gets denser and denser until it reaches that fusion temperature. And for hydrogen, that temperature starts off at 13 million Kelvin, and when it reaches that temperature, all of a sudden it becomes a star. So Universe Sandbox is actually, the physics is pretty darn good, actually. So it's a wonderful thing, you know.
Yeah.
James Dugan says hi to you, Keith.
Hello, James Dugan.
Yeah, D Smith is here. Hey, D.
Yeah, D Smith was over in this chat. That's who told me about that.
Oh yeah, they're saying you're quieter on your stream, but on my stream you're sounding okay.
Oh, okay. Well, I can fix that.
There you go.
Yeah.
There you go.
Fix that. You say Mark is loud on my stream, and I'm quieter.
Yeah.
So let me just mute this loud mouth.
Yes, mute that loud mouth.
Let's see. Hopefully that'll work out a little bit. It's a whole thing between two channels streaming at the same time off of a Skype that we're connected to that has its own, you know, microphone and volume levels, and then trying to patch it into OBS.
Right.
It's two different microphone levels there.
And supposedly there's music in the background.
Yeah, there's music somewhere back there.
Yeah. Yeah, I see music playing back there. I just I'm unable to hear it on my end tonight for some reason. Anyway, I just want to, just before we start destroying things, let's just take a look at what happens with Oumuamua. This is Oumuamua right here. And Oumuamua was a really strange-looking asteroid. It was actually classified as a comet initially, but because it didn't do any things that a comet normally does when it gets closer to the sun, which is to outgas and start shooting off gases and so forth, none of that was seen. So Oumuamua became a spindly asteroid.
What did Oumuamua stand for again?
Messenger. It's Hawaiian, so it's messenger from afar.
Yeah, messenger from afar. That's what it was.
Yeah.
Yep.
I mean, there's several translations of Oumuamua. You know, but in Hawaiian, I don't know how you actually say it. It's like Oumuamua, you know. But it's really interesting, you know, to watch it. So here's Oumuamua, and I'm going to move the Milky Way out of the way. The Milky Way looks beautiful, but it gets in the way. And let's just... I'm slowing down the simulation down here in the bottom. Here you can see now I'm going down to 8 hours per second. And you watch when I hit go, you'll see that Oumuamua is still making inroads here and moving fast into our inner solar system, even though we're going 8 hours per second. That's, you know, it's actually 7 hours per second now. Just over, almost 7 to 8. And you can see what's happening. Oumuamua is coming closer and closer. And as it does, you know, we can actually track it and go right up to it. And people say, well, what's it look like? Well, actually, in Universe Sandbox, they show it as a sphere. It was actually a spindle. It was anywhere from 1,500 to 2,500 feet long and 150 feet to 250 feet in diameter.
Otherwise, pretty big.
Yeah, it was a needle, yeah. Yep. And when it struck the Earth, if it struck the Earth, it would leave, it would create a crater that was several miles across and a mile deep, depending on the angle and so forth. At the speed it was coming, that was the most important thing. If Earth was in its orbit and just happened to intersect and they got struck, it would hit with the force of over 4 megatons, almost 4.5 megatons of energy, and that's actually pretty substantial for a piece of rock that's only about 1,500 feet long. Mm-hmm. So here it goes down through the plane of the solar system and starts zipping around. Now the gravitational pull. The sun, of course, has been pulling it in the whole time, but look where it came from. It came from way above the solar system up there, and now it's coming through the solar system.
Different plane.
A totally different plane, because the plane of our planets is like here, right? Here's the plane of our planets, and Oumuamua came from way up there. You know, basically the northern solar system latitude. So it's certainly not an object in our solar system, and it came through on a trajectory that takes it out of the solar system now. This is a parabolic trajectory, so it comes in.
How certain are they that this thing's actually going to exit the solar system now? Does it move in that fast where they can almost guarantee that it's not like somehow going to magically orbit on a very, very, very long orbit?
No, because the orbital parameters were found with it, and they actually were able to deduce the what are called the orbital elements, and they discovered that it's in I believe a parabolic orbit, meaning it's not going to be periodic. If it was in an elliptical orbit, you know, if you widen an ellipse enough or put enough energy into an ellipse, it becomes a parabola.
Right.
See, So what looks like the focus of an ellipse over here is actually a parabola, which is, it's open-ended. It doesn't close.
Yep.
So it's not orbited, But take a look at this. See here? This is where
the people for levels are good now. I'm thinking they are because nobody has said anything. But I think so. Everybody in P&K chat. I can't see Mark's chat, but I'm hopefully everybody in P&K chat. Is our levels good now? We're even.
Seems like it. I'm gonna pause it right here because this is something interesting.
Yeah.
Carolina Sky. Hey, welcome.
CSA.
Yeah.
Good channel, by the way.
Yeah, for sure. Notice Oumuamua is here, and notice the Earth is here.
Mm-hmm.
Okay, these two objects were not far apart, in a sense. I mean, if you think about it, certainly a lot farther than the Moon is from the Earth. The Moon is well within that distance over there. But when we check that out, we look at how close it is relative to the Earth. That's really not that far away. That's kind of a cosmic disaster that could have been. A
little bit.
Well, I mean, we talked about that on 2 weeks ago. We talked about the biggest extinction events on the planet. They were caused by the flood basalts in Siberia, the Siberian traps. And unfortunately, or fortunately for us, there's no more of those. But unfortunately, we still have these near-Earth asteroids, these NEOs, near-Earth objects, to worry about. This one was a semi-near-Earth object. It didn't really come that close. But this, when you think of all the space in our solar system here, okay, let's be honest, okay, that still feels a little close to me, So it was close enough, if you ask me. So anyway, we'll keep it going now. So Oumuamua came in and it went, and it didn't disturb anything. It didn't have enough mass to affect any of the planets beyond any known values, and it really wasn't that big a deal for us, luckily. But it could have been a very different story. But anyway, that's Oumuamua, and here on Earth, we have our little planet. We enjoy our world. Now it's spinning really fast here, of course, because of the fact that we are actually doing this time lapse here. So we are using 8.5 hours per second here. All right, and that makes things a little bit different. You'll notice. What were you gonna say?
I'm putting my microphone volume up.
Okay.
On my audio device, and it's automatically taking it back down.
Well, I think it's trying to stop you from clipping because you're actually overmodulating.
Yeah, but see, they can barely hear me on mine.
You are kind of low, actually, which is kind of weird. I've got you maxed.
Yeah, so that's what I'm trying. Like my microphone volume in the thing right here, I try to put it up, and it automatically goes back down.
Yeah.
We'll go back up again, and it goes back down.
Well, you got to take off the auto setting.
There has to be like an auto.
Yeah, there is. While you're figuring that out, I want to say hi to Dagger Spells and Most Intelligent Ever Born. I said hi to James and Carlos Huerta. Hello there. And Ken Cantu. Hi, how you doing? And I'm just pleased you guys came out to join us. We're actually doing a Universe Sandbox stream. We just showed you Oumuamua as it goes streaming through the solar system. And then we're going to have some fun blowing things up.
Right.
Because that's Keith's level of entertainment. Because Keith is with us tonight. So we're going to have to blow some things up. And hey, let's be honest. Yeah. It's fun.
Absolutely.
It is fun. It is fun to blow up things. Hey, Spock, move the Enterprise closer. I have to see this.
Okay, it says all that's working.
Awesome.
Yeah, you can continue. I'm going to keep on working on this.
That's okay.
Why my volume keeps on going down.
That's fine.
Yep.
You work on that, and I'm going to sit here and watch Oumuamua leave.
Oumuamua.
Oumuamua instead of Oumumu. Right. It's really cool. Hey there, Joni222. Nice to see you. Marianne, what's happening? I'll be out there to see you again in September to speak at the UFO Congress. Next month, I'm in Norway. I got to speak in Oslo, and Bergen, Lunda. Part of the new science tour that I'm part of. It's we're doing talks on the new physics that's coming out. It's really cool, and it's stuff that reaches everybody. It's not going to be highfalutin, high-powered stuff. It's going to just be stuff that everyone can understand. And we're going to bring this to the U.S. as well, so that's going to be kind of fun. Charles is here. Charles, how you doing? And for those listening in P&K, I'm talking about those that are in my chat, so I apologize.
There are 2 chats open.
Huh?
I said there are 2 chats open.
That's right. The P&K chat and the SkyTour LiveStream chat.
So about you.
Yeah. So Oumuamua came and went very rapidly. And if we zoom out, we can actually see the whole the path that it took. That's Earth. Okay. And it actually zoomed through the solar system very, very fast, and then it gone so quickly. We didn't really see it until after it had passed any possible collision point with us. That's kind of scary.
Hey, I might have done it.
Yeah.
I might have.
You are overmodulating too.
Yeah, I just wanted to make sure. All right, there's my output. Am I overmodulating?
No, that sounds very good right now.
Okay. So people, let me know in the chat. In
yes.
the PK chat.
That
if
sounds
that's
good.
a little louder. Hopefully it is. And if it's not, I give up. But
right.
because I went to the just to the microphone settings instead of the mixer.
Yes.
And set the phone all the way up. So maybe now it'll let me change. Maybe now it'll let me change the what you call it.
I don't know.
Levels. How about it? Nope, it still wants to go back down. Percent better though. Keith is coming in clear. There we go.
Okay, well that's better than nothing.
Ladies and gentlemen, Keith is live with Mark D'Antonio here on the SkyTour LiveStream. Finally. Let's get to smashing some stuff.
Okay. So, what do you want to start with?
Well, you know me, dude. I love black holes.
Yeah, that's true.
And as I was talking to you before we started this stream, I wanted to see what happens if we started taking the smallest black hole, like say the size of a golf ball or a softball, and putting it next to a planet and seeing what it does. Like if it has any kind of effect, or what it has, like how big it has to be to actually have a massive effect on the planet it's next to.
Well,
the object it's next to.
So we can take a black hole that's like let's see, maybe one the size of the sun?
No, make it way smaller, way smaller.
Okay.
I'm telling you seriously, I'm talking like maybe the size of a basketball.
Okay, well we have to figure out how to do that.
Well, you want your mass to be way smaller than
I know.
Or what? Yeah, there would be no mass, but no.
But how do I do that? I want to make sure I can do that here. Giggity. All right, I'm gonna do one thing first. I just added a black hole, and it's an orbit around the sun now.
Okay.
And if I select it, I think I can.
Yeah, there you go.
Change some parameters, and then I can save this.
Yes. Make it small.
Okay.
Well, let it have the mass of the sun, but make it really small.
Well, see that the the physics of black holes don't work that way.
Yeah,
you can't make it have the mass of the sun, but like only be 3 inches across.
I was thinking density.
Yeah. Okay.
Yeah. So like make it like 0.5, and then the radius. Take the radius down to like, because I think you can switch it from kilometers to something else, if I'm not mistaken.
Yes.
You can switch it to Is that really centimeters down there?
What do you want to do it to?
I said, is that really centimeters down there?
Yes.
Okay. Let's click that. Let's see. What's a good size in centimeters? What do you think like is a basketball? How many centimeters?
Well, I mean, we can say 30 centimeters and see what we get.
Okay.
I don't know that it's going to retain its black holiness.
Let's find out.
It's 2 times 10 to the 18th kilograms in something that's the size of a basketball. So I'm going to change this name and say BH basketball.
BH basketball.
Yeah. And I wonder if I can... I was hoping to be able to save this object. I think you should be able to save this object, no?
Probably. Somehow.
Yeah, there is a way to do it.
Earth.
Huh? Oh, I know.
Earth.
Look, I know. Look at the Earth is already... Well, Earth's doing some wacky things. Here's what I want to do. I want to...
Basketball is black hole?
BH basketball is black hole.
And it made Earth do that?
Yeah?
Wow.
Yeah, but see, there's something else I want to do. Actually, now if we look at Earth, okay, we're going to find that Earth is...
Earth is like, I'm out of here, man.
Well, Earth is going to be suffering some climatic changes.
A little bit.
Yeah.
Wow.
Its surface temperature is now down to 10 degrees Celsius.
That thing,
and
that is the size of a basketball. That's how dangerous black holes are.
Well, it's also got the mass of that sun, so
Exactly.
it's pretty bad. Okay. Yeah.
My
So clearly, and we put this out around the orbit of Mars, by the way. That's we sucked it out by the orbit of Mars, and Earth was ejected from the solar system by it.
It just said, see ya.
Isn't that cool?
Yeah.
Yeah. If you look here, you can actually see. Hello. Goodbye.
A black hole cannot form in less than 3 solar masses.
But yeah, of course. I mean, if we're doing fantasy here.
Yeah, we're doing fantasy. We're
Yeah.
doing basketball black holes.
Yeah. You know what I mean? And there's all kinds of limitations we're not talking about. We aren't paying attention to the Schwarzschild radius, okay? We're not paying attention to the mass of the star, because the sun could never be a black hole anyway.
Yeah.
So there's a lot we're not paying attention to. But
wormhole? What's the difference between a wormhole and a black hole?
Well, a wormhole is actually a theoretical warpage of the space, and it could be caused by a black hole.
So you mean from one point in space and time to another?
Well, that's the supposed theory, but wormholes in practice, first of all, we don't really know they exist, number one. Number two, if they did exist, they may not exist for long. They're only temporary. So, and once one forms, it doesn't mean it's going to come back periodically. It's not necessarily true.
Right. Okay.
Yeah.
So now you know.
Yeah, exactly. I want to know how I save it. There's a way to save this. I know there is. Let me see if I can. There's got to be a way.
Big black hole it would take to suck our solar system. Giggity.
I just want to be able to take this black hole and save it, man. Or the worst case, I would just like to, take a black hole in existence and make it, be able to save it. I forget how to do that. Darn it all. That's too bad. How about there's one. Let's bring the Earth back.
Okay.
Yeah. What did I do? Okay, what I did was I actually made another black hole. Come on, get out of there. Get out of there. Stop making black holes everywhere.
Giggity.
Yeah. I made this black hole over here. It's another solar mass black hole.
Zoom in on it. See what it's showing.
Actually, it's interesting how you see. I'll look at BH basketball. Where'd it go? Okay. Let's do that. So if we zoom in, we should be able to. Okay, why am I not able to? Am I in the middle of something here? I must be in the middle of something here.
Must be.
It's going out. And I don't know why that was. It won't let me. Okay, there we go. So now you zoom in and you can see the effect. See, now here's one of the ways that we find exoplanets. Okay, is if there's a planet that's running between a distant star, like the sun is in this shot, and its star, then the gravity of the planet will bend the light of the distant star like this. It'll actually cause it to kind of refract around a little bit, to bend around like this, you see? Mm-hmm. And what this is this is called a gravitational lens. The gravity of the planet, smaller, much by many magnitudes smaller than a black hole, but enough so that you can actually see a little bit of the starlight getting warped like this. And that's how we find planets using this microlensing technique. It stands to reason it'll work, though, because we got so many stars that are usually in the background of the other stars we're looking at. So when we're looking at these stars, that's just something went by just now really fast. We can tend to see a disturbance that occurs because of the gravity well. But that's kind of right, you know.
Now, we were just looking at Uranus through a black hole. Giggity.
Giggity, yeah.
A black hole. But you know what? I mean, how does that compare to like a water droplet? How it distorts? Because like, say if you have a water droplet and you have like an object behind it, you know how it distorts the image. It's not really bending the light around it, but it's actually the water droplet itself is playing with the optics.
That's refraction, yeah.
Okay. So
yeah, very different thing. Refraction is bending of light going when you go from one medium to the next, like air into water. But bending light in space is a very, very different thing. When you're bending light in space, you're actually, you're actually warping the space-time continuum. You're warping the fabric of space. That is the interesting thing. When you talk about light, for instance, like we go back to this black hole, right? When we look at this warpage, you say, well, what is that warp? What are we looking at here? Okay, and I'll use the galaxy. See, now you can see the gravitational lens. This is essentially the image we saw from the 55 million light-year distant M87 galaxy. This was the image we saw. If you remember, it was like a disk around the center, and they said, look, this is the black hole itself. What it was it was an artifact that was created by the warping of the space by the black hole. And the black hole was what's smaller than this, but the warp was out here, because there's a certain radius in size that a black hole will be based on its mass, and that radius is called the Schwarzschild radius, and you can calculate it based on the mass of the star that made it. And if you can calculate the mass of the black hole, you can calculate roughly what the original star must have been in mass. And they're all going to be several times the sun to begin with, because nothing smaller than that can be a black hole. It'll become a dumbbell nebula or a ring nebula. It'll become a planetary nebula like that, where it swells up and sloughs off its outer layers, you know. But this is cool, you know.
Fabricio in P&K chat says, I think the supermassive black hole at the center of the Milky Way galaxy is 4 million times the mass of the sun. He said, correct me if I'm wrong.
Okay, I don't know the exact mass of Sag A, that's Sagittarius A, but let's do this. Let's actually find out. We can do that because we shall now go back and go back to opening. I want to show all of these. How do I do this? I don't want to just show Oumuamua. Let's get rid of that. Okay.
By the way, if any of you wanted to get this, it is a game off of Steam, like quote unquote game, but is a physics engine. It actually applies real physics. It is nice to have a computer that can handle the calculations. It does take a lot of CPU because it is a hefty program to run on a computer.
It is.
But it's something that you can get off of Steam. I think it's like $12 or $14 for this for Sandbox 2.
Yeah.
And you can spend hours creating planets, smashing stuff into one another, making galaxies collide, building suns.
And we will. We
definitely
will.
something you can get if you want it. And you have a powerful enough computer.
That's right.
To get.
That's right. It's a beautiful, it's a wonderful program, and it's a lot of fun too. And let's just take a look across the top. These are all the different types of things you can get. There's some core simulations with this, okay? Things like our solar system right here, okay, which I'll bring up, okay? And, okay, so this is like a base one. This is our solar system, and it gives you a little write-up about what, about the solar system, what little it says is enough just to get you having fun, okay? But then there's others. If you go across, you'll see that this is the core simulations. There's a bunch of those, all right? And, colliding moons, 100 colliding moons, sphere of moons, a binary pulsar. What do those look like? And the physics is all...
Colliding moons?
Yeah, colliding moons. You want to see that one? We'll do that.
100 colliding moons. Let's see what it looks
like. We will. But then we have galaxies. Look at this. It has galaxy simulations. This version, if you're on Steam, if you have it on Steam, it's updated. This one has just been updated to add more galaxies outside our own. This is our Milky Way center right here. We can pull out of this and go all the way outside our galaxy to see all the galaxies around us too in this simulation. We can look at all the different physics things. Like here's a bunch of them: the Earth and early Moon, back when it was first formed. Saturn and the Earth. Okay, some of these are real, some of these are not real. Okay, we're talking about
theories of how they would work, according to the math.
Yeah. And then here's one, when you have tidally locked Earths that are close to each other, what would happen? Okay. Oh, believe me, we're gonna have fun tonight. We're gonna go back and check these out. Collisions. This is where Keith likes to live.
I don't think I've ever watched any of the simulations, like the, I always created my own and started throwing stuff at planets.
Yeah.
So it'd be nice to see what they actually come up with and see how cool it looks.
Yeah, and it's a community out there where you can put them in. Like here, if Mimas, Saturn's moon Mimas, collided with the moon, okay, and in slow motion, this is what it would look like. Okay, Earth and Apophis. If the asteroid Apophis hit the Earth, okay, Earth and the moon in slow motion, and you see what happens. The devastation. Here's the thing: when a planet is struck by something else, a lot of things happen. It doesn't just make a crater. It throws a lot of stuff up in the air, but that stuff it throws up in the air is very hot. It's all melted and molten, so the planet globally is going to heat up really, really hot. And I think, I think that's pretty. I think that's pretty intuitive when you watch it in this simulation. You could throw Earths at Jupiter, and all of a sudden Jupiter is now red hot. And it makes sense because there's a lot of energy expended, and the heat of motion, the energy of motion, the kinetic energy, okay, which is calculated as 1/2 the mass times the velocity of the object squared. That motion is translated into heat, and that's where it goes when it strikes something. So the faster it goes, the hotter it gets.
It did, and I noticed there's a way on here, because I've done it before, is you can actually make Earths and planets other than round, and it shows you in slow motion, like what, based on the physics that we know, that we use day in and day out. Like if you make a donut Earth, it shows you exactly what would happen to it once you play the simulation.
Yeah.
Once again, you could do the flat Earth if you wanted to, and show that the gravity would just crunch in on itself.
I would like to see that one. We're gonna find that one tonight. If it's here, I'm gonna see it.
Create your own different shape. You can even try cubes, I think was on there. Once you get to a certain size, that gravity just becomes so strong it just pulls everything in.
Yeah. Oh, Carolina Sky asked a question. This program, can we see the exoplanet named Goblin? Yes, we can. Actually, there's a simulation in here for the Goblin at the end of our solar system. And we'll show you that too. I'm just showing you here some more collisions. And then there's a bunch of different solar system things. and then potentially hazardous asteroids within our solar system.
How about that? You can make your own solar systems.
Oh, you can. You can. Be honest. You don't have to take what they take. You can make all your own things.
Yeah, you can do a 30-planet solar system.
Yeah,
if you want to.
we can look at the evidence for the 9th planet based on all the gravitational perturbations that are out there. I mean, that's really cool, you know? Really, really cool.
Give them their own orbit.
Huh?
Give all the planets their own orbits that you want. They don't have to be like, you know, on the same plane. They can be crazy all over the place, just missing one another.
You know? We're just looking at things that people did. So
just the computer power. That's all.
You know what's happening? People are saying, "Well, stop talking about it and show us, man."
Yeah.
Right.
Shut up, Kate.
Just let's do it, and we're gonna. I'm just showing you so you see different types of planets. Okay. And then you can do exoplanets too. So there's a number of exoplanets. Now, some of these are community generated, so they may not be perfect. But then there's a bunch of historical things. You can go watch the Parker Solar Telescope pass the sun. You know, accurate. The Parker Solar Probe. Watch it. It's accurate. Okay. This is the one that Carolina was talking about. The goblin at the edge of our solar system. Okay. Let's just start that one up anyway because he asked for it.
Yeah. Let's do it.
All right, well, there it goes. Okay, now this is talking about in October, how October of 2018, they found this distant object. It's a TNO, a Trans-Neptunian object that's out there, and it was designated 2015 TG 287, 387, and that was called the Goblin. Yeah?
I see. Yeah, I see.
You see it?
Yeah, it was kind of hard right there for a second because it's one of like a light, not white color.
Yeah, well, does that make it easier?
Yeah, that's perfect.
Okay, because this is it right here.
Yep.
Bingo, right there. Yeah, and so it has an orbit that's crazy because it's really elongated or elliptical, and it can go all the way out to 2,300 astronomical units distant from our sun. Now, that's pretty cool. To have found that, and you can actually see this really long orbit out there. Okay, well then you might say, well, what's this orbit over here? Okay, and that's, I believe, Sedna. Okay, so Sedna also has this extremely long orbit as well, and elliptical orbit. And the Goblin was another one. So these are, again, TNOs. What are they? Well, they're most likely going to look just like comets when we see them, most likely. And this object here, I don't know if they have the parameters for it in here. Well, let's find out, shall we?
Why do they call them Trans-Neptunian objects?
Because it's an object that's an object along with a whole family of everything beyond Neptune that are beyond Neptune. They're in the Kuiper Belt, but they actually have these elongated orbits. And they say Trans-Neptunian because they're just beyond Neptune. And you might say, well, wait, everything in the... Huh?
Would Pluto be considered?
Yeah, actually, Pluto was called a TNO as well. Okay. But in fact, we can't technically call it a TNO because of the fact that it does come inside of Neptune's orbit at one point or another. See, because of its ellipticity, the way its elongation is, it'll actually come within Pluto's orbit. I'm sorry, Neptune's orbit for a small period of time.
I say make Pluto a planet again.
I agree. I told you I sat with Clyde Tombaugh, who found Pluto, on a grassy knoll in Vermont, and he was going to be doing a talk, and I basically was up there at this astronomy get together as well. And this was many years ago, and he was elated to have a planet that he could find, that he found. And when he asked him, I asked him,
not
like,
very big. I mean, I get it. It's not, your classic planet, but you know what? It was part of our 9 planets for the longest time. Yeah. And then we get past it with some cameras finally, and it's just showing a big heart and its own little moon. And you're like, how can you not just give it an honorary planet name?
Yeah. Well, you know what? It's not just a moon. It has 6 moons.
Yeah.
So let's be clear.
And the Mass Effect is like a little less than a light year away.
And what?
Mass Effect.
Mass Effect? Yeah, I love that game.
That's Relay was supposed to be right beyond Pluto.
Oh.
Or the moon of Pluto. What all these years they thought was a was a moon. Turned out to be the mass relay. It was encased in rock.
You're gonna confuse people.
Yeah, I know, right? That's a great game. I love it. The original.
Yeah. Hey, Gas Mask, welcome. Hey, Astro Live, good to see you here too. Yeah,
Astro Live is a good channel.
Huh? Yeah.
Astro Live's another good channel.
Exactly. I'm trying to also see who's out there. So pardon me for not. I'm jumping in the chat. I am checking out the chat. Gas Mask, this is Universe Sandbox 2, as you said. Yep. Yeah, and it's a really good. It's $25, he says, and that's probably true.
Yeah. Sometimes they have it on sale for special occasions and whatnot. And I think I got mine for like 14, and it was on sale one time. Yeah. So keep an eye on it. If it drops down below $15, definitely grab it as long as you have a computer that can power it. And,
you definitely need to have a powerful computer for it. It really does need to be powerful. Even this computer. This is a,
say an i5 or better. You think?
Yeah, i7 probably best.
Yeah.
And that's the old family of processors. There's faster ones now, I think. So, but yeah. So this I brought this up just because Carolina Sky had asked about it, and that's the object out there. It's really they call it the Goblin, which is kind of funny. But look, we have all kinds of other simulations here, that we can run, and this is just in the historical ones. In the historical ones. We can check, for instance, the Parker Space Solar Probe, the Parker Solar Probe. Mm-hmm. Okay, and in August of 2018, this one went up there. It's studying the sun's corona. Okay, but the fact is, it's actually this is showing you an accelerated time lapse of where it's going and when it was launched. So here's the Parker Solar Probe now. All right, so we're focused on that. So we're connected to the probe. So we launched it from Earth, and off it goes. And this is the projected orbit. Okay. And if we increase the time it takes a little bit, you'll see what happens. Venus, does its own little chugging on it, and Venus gives it a little gravity assist. And helps align it. We actually can. It's just so cool how we can use the other planets' gravities to assist us in getting these probes to where they have to go. And then studying the solar corona. I mean, it's going closer to the sun than any other probe we've ever developed. I mean, and much closer than Mercury. See, this is Mercury's orbit here.
I'm going to give you a heads up. My OBS conked out, so I just told everybody to come over here.
Oh, what do you
I'm
mean?
not sure why it conked out. I have to reset it and everything.
Oh man, why did you do that?
Sure why.
So your stream dropped?
There, so.
Oh, okay.
Yeah, so I told everybody to go over.
Yeah, no one likes Universe Sandbox,
I love it. I like these things.
So you can see the Parker probe is pulled into this orbit around the sun to go circling around the sun. Very, very cool. And safe too. We've got it in an orbit that's safely away from other planets. I know the lines look like they're close, but they're absolutely not. Yep, and there it is.
Yeah, everything's just like, it's where a lot of people get messed up with the moon too.
Yeah.
Like everyone's looking at the moon, like, why don't I see all these satellites or space junk flying by? And they don't realize like how far we're actually zoomed in on the moon, where the small amount of sky they're actually looking at. Like with this, you're like, oh, well, look at all the planets, nice little souls. I mean, this is millions of miles across.
Yes, the distances are massive between them.
Yeah. So now I'm officially watching the SkyTour chat.
Are you? Okay.
Yeah, since I shut down the P and K.
Okay.
I think I have to update some stuff on that. I don't know. Either way.
Interesting. Gas Mask asked a question. Can you talk about how time travel is impossible because you would have to rewind or fast forward the universe to do it? It's a hot topic in the UFO community. Yeah, I'm aware, Gas. That's true. Other than storming Area 51, that's the silliest concept I heard so far. Let's all storm Area 51, and the same 6 people will show up at the gate every time, you know, and they'll get arrested again. It's like, all right, well, we did it. They said to, so we did. I know.
Yeah, that's the whole thing silly. I don't think people realize. Well, a lot of people realize it was started as a joke, but
yeah,
there's going to be some people that took it seriously and are just going to be sitting outside waiting and do something stupid if they want to get arrested, and then it'll slip everybody's mind.
And then they'll complain about it, saying, "Why did I get arrested?" Astro Live, yeah. Universe Sandbox 2 has come a long way from Universe Sandbox 1, and we have yet to even broach the surface. This is the Parker Solar Probe we're looking at now. You can see here, and it's actually pretty detailed. This particular 3D model is taken from NASA's 3D model repository, which you can get a hold of and then 3D print the darn thing, which is kind of cool. I've gotten several and 3D printed a few. I'm actually working on a Navy ship right now, and I'm model, and I'm for the Navy, and I've been 3D printing a lot of it, and I need to take a break because I've been doing this solidly for like 3 days straight, and my head is tired of 12-hour days, So, but it's okay. So there's Parker. Parker's set up in a little orbit. We watched it zip into this orbit from Earth, and now it's sitting there and doing this thing. So that was kind of fun to watch. And now, but Gas wants to talk about time travel. Okay. And I think that's interesting. If we were to have time travel, everyone thinks about time travel on the Earth, going back in time, but they don't realize, well, what about the universe? If you are going to go back in time, and this is a topic that Gas Mask, to be honest, we have broached before, but the fact is, when we look at the fact that going back in time on the Earth means you also go back in time for the universe, doesn't it? And the question is, where do you draw the line? How do you separate? How do you make the distinction between our time and the time of the universe? And I think the answer is that you cannot. Now, I'm on a science advisory board with a particular one professor whose last name is Mallet, and he ended up in a lot of prestigious magazines because he has actually invented a time machine, and it uses a special set of lasers. And as long as the machine is on, you can go back to any point in time and get information. All right, from any point, from a time that any point in time, starting from when the laser was turned on. Turn the machine off, it's zeroed out, and you got to do it again. So could we go back to 1800? No. But if we turned it on in 1975, could we basically go back to 1975? The answer is we could go back and see information from 1975. Does it mean we travel to 1975? That's the fuzziness here. Mallet might say, in a sense, yes, but not really.
Is that almost like watching a movie from 1975?
Yeah, kind of, sort of. But the thing is, he's a really interesting guy. Nicest guy on the planet. Okay, which planet? The one that's circling. Right here. There, nicest guy on this planet right here. That's the one. That's the one. That's the nicest guy on this planet right here. On Earth. Yeah. So, yeah. What's that?
That blue little marble.
All right. The pale blue dot, as Carl Sagan used to call it.
We're so insignificant.
Yeah. Now, here's another one for you. This is actually the solar eclipse from 2017. Here's the shadow. This is what it looks like from space. This is actually approximately what it looks like. I'm going to slow it down. Okay, so now we're doing, 1 minute per second. You can actually see that the sun's shadow has been caused by none other than our moon. Okay, which is right there. All right, and we're seeing the moon shadow caused by the sun, and you can actually see how this eclipse was moving across the planet at that point. Do you remember that eclipse?
Yeah.
Yeah, it was amazing.
Mm-hmm.
It was beautiful. Yeah, so that was kind of a cool one.
from South America. That was a beautiful one as well.
Which one? This
From,
one?
We had it from Chile. No, just last week.
Oh, yeah, right. I was gonna say, yeah, that was this past one. Yeah.
Yeah, beautiful.
Yeah.
Great weather down there for viewing.
Yeah. Very nice.
I set up in Argentina. We were linked into the one from Chile. It was
Okay.
amazing. They did a really good job with it.
Yeah, I watched some of it with you.
Yeah.
So let's see. So we got some other things here. Let's go back to some of the fun stuff. How about some collisions?
Kaboom.
How about the moon and Mimas in slow motion? Ready? Mimas is a moon of Saturn. Okay, and that was kind of a, yeah, it was slow motion, but it wasn't. It was kind of quick. All right.
Liquid magma.
Yeah. Lots of magma. Yeah. So let's see what it looks like. This is the moon here in Mimas, and this is the extent of the shock in the rock that's being felt, and you can see all the particles that are coming off the moon right here. All right. This is essentially what would happen. Now, all of those particles are made to go airborne, and you'll see that they leave some streaks, but then some of them are going to come back and they're going to make secondary impacts on the moon. All right. And because the moon only has 1/6 the gravity of the Earth, all right, and let's increase the speed here a little. Because the moon only has that lesser gravity, well, a lot of these particles are going to escape. And where would they go? They'd come to us, most likely. Some of them would.
This is a form of more gravity.
Mm-hmm. That's right. And there's an argument too that the moon shielded us from asteroid hits in the past, and my argument is actually the opposite. The moon actually helped bring them to us. The moon was in part responsible for the extinction events on our planet, because it caused it's a second gravity well. Yeah. So you see, there's this moment in time with these collisions where the moon seems like it's safe. All right. But over time, okay, some of these particles will end up coming back and striking the moon. And I'm gonna. It might take them some time. All right. Well, I haven't seen any of the secondary impacts yet. It might take too long. I mean, they have to go out and expend their energy, and then if there's no other gravity well nearby, then...
Well, you're still under minutes per second. So
yeah, I know.
If you said like hours per second, maybe it would...
Yeah, then we'd see some.
Depends on how fast they had the velocity of it hitting, too.
That's true. Oh, there goes one. Boom. See, there's another one. Boom. Okay, did you see that? Another one came back. Yeah. So some of them are in orbits that are going to make their way back.
Oh, I guess they didn't have Earth in this?
No.
I was going to say it'd be pretty neat to see where they actually went.
Yeah. Well, we could actually make our simulation.
Yeesh.
What's that?
That impact crater on the moon.
I know. Look at that, huh? It's a new one. Look at that new impact crater. Yeah, I mean, I like this. That's what I like about the Universe Sandbox. They actually, it never used to actually create new craters. Okay, it would actually just bring the moon back to what it was. But the new version now has added you can actually smash a planet to smithereens. It's really pretty. Okay, let's see now. How about all right, now here's another one. Here's Earth and Ceres. Now Ceres is a asteroid it's actually a dwarf planet in our asteroid belt. All right, and I'm going to slow it down because I'm going to show you what will happen when it hits. Now Ceres is actually a pretty good size. All right, and it'll never come into the inner solar system. There's no way that it would. All right, but let's just take a look. Ceres has a size of literally, 9 times 10 to the 20 kilograms. So it's not lightweight. All right, and it's 470 kilometers in size. And if you want to know that, that's the radius. If you want to know it in terms of, let's see, in terms of, where's my miles here? Why don't I see miles anywhere? I could calculate all that, but I should just be able to do it directly. Okay, I guess they don't give you that. You can do it in terms of other planets. All right, okay, so it has a radius of 470 kilometers. All right, and we've slowed it down, and now, okay, it's going to hit, coincidentally, right. It's not going to hit the Yucatan, but it's going to be close. So here we go. Let's watch what happens here when Ceres now comes in and strikes Mother Earth. Okay, let's slow it down a little bit. Here we go. Oh boy. Okay, now right away you see the shock wave passing through the crust, and read this as tsunamis in the ocean, and secondary impacts, tertiary impacts. See that? All the secondary and third impacts.
Very fast evaporation as well.
What's that?
Very fast evaporation.
Yeah, well, I mean, it's also going to be superheating a lot of our atmosphere. See that? So if something hits that size, it's going to do a number on us. Okay, and watch these shock waves, okay?
Watch the planet, too. Don't you have a little planet thing where it shows you the planet changing?
Yeah, that's this right here.
Yeah.
Yeah.
On the top right, you can see how our planet changes then.
Yeah, you can see there's the impact site. The major impact site. And you can see the secondary impacts. You can see them coming back. And those show up as the other bright dots here.
Because our gravity is low.
Because our gravity is pretty high, yeah, high enough. And what happens over time, okay, other impacts occur.
Look at that.
Yeah, okay, so that's
all the dust and the nasty.
Yeah, it's all the particulates that escaped in the Earth's atmosphere that escaped. That's pretty bad. Yeah, and that stuff would just go out into space, and in other words, at the impact speed, a lot of that stuff went off. And if you speed this simulation up really fast, then it gets inaccurate. All right, if you run it slow,
unless you have a very, very, very good computer.
Yes, that's true. Very true. But in this small inset, you can see the crater.
Yeah.
You can see the crater that was made by that impact.
Well, even on the bottom it says simulation can't run any faster recurrent settings.
Yeah. I mean, yeah, and that's why I'm leaving it where it is.
That's actually really good.
Yeah, no, it's running nicely here. Okay, so we come in here.
Look at that land forming.
Well, look at this too. The surface temperature is 360 Celsius.
Water is evaporating. More land is showing up.
Yeah, look at it. See?
It's crazy.
Well, it's boiling.
Yep.
Yeah.
And we're dead.
Well, look at. See, here's water right there, and it's gone.
And we're at a surface temperature of 362 degrees Celsius.
Right here, yeah. Yep.
I would go to Fahrenheit on that for most things, so not a lot of people know. So, well, I guess
680 degrees. That's the average surface temperature. So you see, that would actually, if you look at the Earth over here, this gives you a better feeling for what happened to the Earth. All the water was boiled away, even though the impact was on this side of the Earth. So the question becomes this, right? What if we have, say, just an Earth and Moon, okay? All right, colliding. Okay, now there's another one. Okay, you see this? Ceres is 480 kilometers in size, I believe. And look what happens to the Earth when the moon hits. If the moon hits. The entire Earth is rendered molten once again.
And we're dead.
Oh, we were dead long ago. I have to say, okay, these are the secondary impacts. See what happens?
Mm-hmm.
Yeah. And these are all fragments. Each of these little things are fragments. These little circles are like fragments. Here's a fragment going around. Boom. Okay. And for the simulation to run properly, it has to make discrete fragments. Okay.
Being that it becomes molten again,
yeah,
does it increase its magnetic field because of the movement?
It can recrystallize the iron in the. You see, the iron in the core is solid, iron and nickel. But if the core is the outer core is molten, and then the mantle is sort of a plasticky, semi-molten state. But the magnetic field, those iron crystals will realign, and it's possible that it can generate either more or less magnetic field. Depends on a lot of things, and I think that what it depends upon the most. What's that?
It has a new moon.
Yeah, actually, it's got that little fragment.
It's going just the right speed where it's not being sucked in.
Yeah, not yet. Let's see if we can actually. Let's see if we can follow that.
Those are new people.
Let's see if we can follow that here. Let's speed it up. Let's speed this up.
Well, actually, click on it, see what the size of it is.
Oh, look, it already crashed.
Darn.
It was a decaying orbit.
I saw that simulation up there that said Neptune and Earth. I never thought about that one, but that one would actually be pretty cool.
Neptune and Earth?
Yeah.
All right, let's see what we get. Neptune and Earth. Whoa.
Ooh, look at that.
Yeah, you know what's happening? You know what? I know those of you in my chat, you guys are smart. Do you know what's happening right now? Why do we see this dust? What's the simulation telling us this is? Yeah, it's a little test, little quiz. The answer, I'll tell you. Okay, this is we're within the Roche lobe. That is the limit to where the planet is so close now to this. Our planet is so close to Neptune that Neptune's gravity is starting to rip apart the Earth. All right, so tidal forces are now ripping the Earth apart. It's the reason Saturn's rings never formed a moon. They could never. The differential gravitational forces on all the particles was such that the particles on the side facing the planet, that is to say, if there was a moon facing the planet, that side would be torn at a lot harder by gravity than the other side facing away from the planet. So that's why planets would in fact be torn apart if they're too close to each other. And that's what we're seeing here. Let's slow it down and watch what happens to Earth. This is kind of interesting when you watch this. This is 30 seconds to a second. Okay, the tidal forces start acting on the Earth, but then as it gets closer, you'll see something else happen. Okay, now it is going to be colliding with Neptune, and when it collides with Neptune, we start to see the collision. All right, and it's colliding. You see the collision now, and look at you're seeing the same waves on the Earth. We're seeing a shock wave spreading out in the same way. Earth vanishes into Neptune. Okay. All right. And you might say, wait a minute. Neptune swallowed the Earth. Except that in the instance where a large planet like the Earth collides with Neptune, the other thing that happens is Neptune is going to heat up tremendously. And as we accelerate some time here, you'll see that Neptune begins to heat up to the point where there's a scar for where the Earth hit, but Neptune should heat up and become molten itself. Not molten, but it should get incandescent. And I'm just waiting to see. There it is. I just had to go some time.
Sweet.
Yeah. So Neptune would become incandescent, not like a star. It wouldn't become a star, but it would actually become a very visibly red planet. From heat.
Dude, that's crazy. Why would it make lines like that?
Those are just the cloud bands. They're just figuring that the clouds would actually form these striated bands. Mm-hmm. It's not necessarily actual, because Neptune doesn't have bands like this, quote unquote. But if you look at Jupiter and you throw something at it really large, like Uranus or something, you get the same kind of thing. Just incredibly awesome. Now, this is my favorite. This is a fan favorite. What would happen if we toss Mars at the Earth? Well, first of all, what I'd like to do is figure out... Oh, where was it? How can I... I'm trying to slow down the initial speed of Mars. And I don't...
I think you have to click on Mars.
Huh?
Click on Mars. And then click over on its settings over there.
Yeah, I don't know that... Well, maybe. Let's see what we got. Let's see what we got here.
It should say velocity somewhere in there, I thought. Oh, speed right down there.
Oh, yeah, 10.7. Oh, maybe that's this. Let me just try 5.
All right.
And see if that changes over here. It did not.
Pretty much anything bigger than, say, 5 miles or 6 miles across is pretty dangerous for the Earth.
Oh,
it's
yes.
Going to cause major damage.
Oh, yes. Okay.
If not, extinction level.
So here we said 3 kilometers per second. Now, if Mars struck, you might say, well, everybody on this side of the Earth, over here in Saudi Arabia, in Madagascar, they're going to be just fine. You know,
seen the moon.
There'd be worldwide earthquakes. But then you got look at the shockwave. Oh, my.
The shockwave itself is going to kill millions.
Well, look at it. Here's the shockwave. See what it's doing?
Oh,
Shockwave.
What? What the heck is that?
Oh, those are that's Universe Sandbox way of simulating large chunks of the planet that got thrown off at some velocity.
That's pretty cool.
Yeah, but those are coming back.
The fire tornadoes.
Yeah, well, don't forget. Okay,
Avenge.
They're coming down now. Yeah, these vengeful little critters are coming down. Oh, there they go. They're drilling their way in. Kaboom. And they make
a lot of computer because YouTube just slowed to a crawl when it collided.
Really?
Yeah, it's back to normal now.
Okay. Look at that, though. Yeah. Look at boom, 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 boom. It's like peppering with all these additional strikes. Yeah. And you might say, well, the people in Madagascar might have survived. It might be a cloudy for them, but didn't they survive? You might think, let's move to Madagascar. We'll be safe, right? Well, if you just keep watching for a little while, you'll notice something happening. And you'll see that a lot of the impacts are striking on the other side of the planet now because some of that debris came out and back. And that's sad news for the people in Madagascar. Okay?
And the oceans are drying up.
And the oceans, again, are going to dry up because if we look at the Earth information here, we can see that the temperature is now 415 Celsius, or 775 degrees. Thank you very much. And let's just crank up the simulation here. And the temperature's coming down now. Okay, but look, there goes our oceans. See that? See that? Look, Africa, the Mediterranean's almost gone, and it's gonna be gone. There it is. All right. And now you can see that Asia, Saudi Arabia, and Africa are all connected as one landmass. Now
even though it is cooling pretty quick, it didn't take it long to evaporate pretty much everything.
Right, and if you notice the temperature is dropping now, okay, let's take this to a logical conclusion. Let's keep going to as fast as we can go. All right. See what it looks like. And you'll notice that the temperature, the impact area stays pretty hot. Okay, now we're down to 400 degrees Fahrenheit. And we are dropping under 400 degrees. It's long since a dead planet. You also notice that Earth's rotation is all different now. You notice?
You gotta realize too that that's only like 3 days after impact.
Yes. And check out the rotation. The rotation axis has been all messed up from this impact. Yep. 300 degrees.
Water has been formed.
Yeah. Now, the other thing is, water will come back.
There it is.
Yeah, water does come back. But it doesn't come back to the same type of planet we had, notice?
Actually, yeah, let it go for a little bit and see where new oceans form and everything.
Oh, yeah.
How much new...
it's a whole new planet.
Yeah. It hit the reset button.
Yeah. Yeah.
Look at that. You can kind of tell some old continents.
Yeah. I'm not sure.
That's Africa.
Yeah, but
man,
look at the rotation, huh?
Yeah.
Yeah, look, the United States doesn't look anything like it used to. There's still a lot of land mass. If we looked at it the way it wants to orbit this way, I mean, that's the way it's rotating. So the impact actually changed that. Now we could launch a massive thing at it just like this and change the rotation once again. Of course, it'll make it red hot, and we'd have to go millions of years ahead.
That only 16 days, and it cooled all the way back down to 218 some degrees, just above 200 degrees.
Yeah.
That's still really warm water.
Let's keep going.
Let's see how long it goes until we get it under 100.
All right. Well, here we go. We're actually at.
Okay, so we're just about there. It took, was it 118 days?
Well, the average temperature on the surface of the Earth, though, is nowhere near 100 degrees.
No, I just wanted to see how long it took to get to 100.
I think that's actually what's called the equilibrium temperature. I'm not sure.
So let's just do, let's say 60.
They're calling it average temperature on the surface. It's probably equilibrium temperature. And equilibrium temperature is typically a lot lower than what you think. Okay, and look, we're all back. The lights are back. Yeah, well, we all recovered, folks. See that? You know, it's this is just one of the things that the simulation doesn't do, and that's the continental plates are the continental plates, and you will get water back again. Why? Because our planet has a way of it makes water automatically. It's delivered by asteroids and so forth. But certainly bringing water back like this is something that would not happen just like we see it here. So why it does it, I don't know. It's something I haven't figured out yet. What else would we want to do here?
I don't know. There's so many simulations to look at.
Yeah, there's so many more than there used to be, too, you know. What happens here? This is Earth and Ceres skimming each other. Well, that doesn't look like a skim. Well, maybe it can be a skim. Let's slow it down just to watch it. 26 minutes every second. That's good. Now let's see what happens here. What if you saw this shadow over your ship? Oh my god! And then it's like, uh-oh.
Well, that's not a skim. That's an impact.
Yeah, that's an impact. But look what it's doing. It's shoving a massive amount of stuff out of there.
Into space.
Yeah, look at. See, folks, this is fun. Okay.
I wonder if that would be a round crater.
Yeah, but look at it. This is one thing it still does, which I didn't like. It comes out. It comes out as a round ball. Here's what it's trying to do here.
Well, it might have been big enough where it's.
Well, it would have been broken to pieces. The thing is, it would have come out.
Once it came out, like the initial velocity came out, back out into space, it just, all coagulated back into a ball again.
That's kind of what they're trying to simulate, that its own gravity pulls it back together. But that doesn't really work for me. But you know what? You gotta like the visuals.
Yeah.
I gotta tone down. I gotta figure out how to get rid of all this debris, or at least make it a little more transparent. Because they're proud of it, they like it, but it's somewhat realistic that we'd be surrounded by a dust cloud of our own debris. But I think we gotta tone it down just a little bit.
Live wants to see Venus hit the Earth.
Really?
Yeah. Well, that's two planets the same size. Which one wins out?
I guess that we're gonna have to see that, and let's do that.
It's probably in a simulation somewhere, you would think.
Maybe, but why not just make it?
You can.
Yeah, actually, let's do that. Let's say planets. Let's bring up the Earth and Moon system. Okay. Here's an interesting one. I like this. I'll tell you why. Because people don't realize just how far the moon is away from us. See the moon out there? Look at that little tiny moon. And people say, well, they see the moon so big in the sky, that can't be right. Well, it actually is quite right. Right? And if you want to see it, this is kind of what it looks like. Right? That's what 240,000 miles looks like. Right there. And if we want to take the moon and remove it, now we have just the Earth. All right. Now, if you want to see what happens when Venus hits the Earth, then we have to go to, let's see, is it under Sim? That's Collide. Oh, I don't know about Collide. Oh, enable collisions. They're enabled. Never mind. Under Tools, maybe? Yeah, there it is. Launch. And here's Venus. You want to see Venus, huh? You want to see Venus? Look at the size. Okay, you sure you want to have Venus launch at the Earth? Okay. Yep. Shall we?
Yep.
Okay, here we go. All right, so Venus is launching at the Earth now. Teehee, I don't think it's going to be good. Oh. Yeah, I'm afraid that's what happens.
Dead.
I think we're all dead.
Let's see what kind of planet forms. Wow, look at all the sparklies.
Oh, yeah, look at all the sparklies. I know, right? Yeah, as you can see, we are not going to survive that.
Yeah, let's speed it up now and see what it looks like. Watch it just come out looking like Earth.
It probably will.
But I wonder if the measurements would change, like the mass and everything like that would be changed.
Actually, that does change. That's something that they do change.
Cool off Earth.
Yeah, it might.
Well, years per second here, people. So this is 10 years after collision.
Let's bring it up. Years per second. Okay. There we go.
Years, finally, we're cool. Okay, let's stop it right there. Let's see what it's looking like.
And it's, whoa, there's a crater.
Whoa, is that really? Oh, wow. Click
That's
on
a
that.
crater. I don't know if that's even valid. And look, life has found its way back. Oh, that's not true.
Lizard people. It's
look at that.
cockroaches. They have evolved.
That's right. Your cockroaches have evolved. Yeah, here's the new planet.
Wow.
And that must be one of the main fragments from the impact.
Yeah.
Wow. That's pretty interesting.
That
I don't necessarily buy it, but huh?
Venetian crater.
Yeah, that's right. Venusiu. We'll call it Venusi.
Venusi crater.
Venusi crater. Neat.
Wow. And it's like weird because all the land is like on one side.
Well, kinda. I mean, it's just that we got a thicker atmosphere. It's a blue haze now.
Yeah. What's the temperature on it?
Oh yeah, that's a good question. Let's find out. Temperature on the surface is minus 30 Celsius after 1,800 years.
It looks like it did.
What?
It knocked its orbit.
Well, we don't know what its orbit is, but we know what its rotation.
I was thinking that. I mean, something like that. Two planets, you gotta have an orbital.
Oh yeah. But we only showed Earth. We didn't show the whole solar system.
Right.
We can do that. We can do that. Oh, we can do it too.
What is minus 30 Celsius? That's what?
Minus 30 Celsius. I'll show you right now. Minus 30 Celsius is minus 22 Fahrenheit.
Cool off with a vengeance.
Well, actually, the equilibrium temperature on the planet is not very high. So it's a funny temperature value. You gotta get used to it.
Look at that. Why is it so shiny? Just because of ice?
Yeah, I mean it's minus 22 degrees, so it's going to be a lot of ice on the planet. See it?
Ow.
Yeah, it's all frozen there. I like the new version because it actually does attempt to make and show some really cool new features,
Right.
I mean, you don't even see the United States anymore. It doesn't exist because the land masses were moltenized and then brought back. I love it.
Well, you figure depending on how fast they hit, you figure that collision of Earth and Venus, how big of an explosion that would make.
Yeah,
like
the two
we'll be
planets
finding
would
pieces
merge.
of both of those planets on other planets, like Mars, and just caused by new meteorites flying off this now combined planet.
Yeah.
Now what are we gonna launch at it?
Ooh, I'm gonna do something else. Let's look at the moon. Grab the moon. Okay.
All right. Real quick, I'm gonna refill my drink. I'll be right back.
All right. You're gonna miss it.
No, I'm still watching.
Okay. Let's blow up the moon.
Blow up the moon.
Yeah. Okay, why is it not exploded? Oh, I know why. Here we go. Boom. So if the moon was to be blown up, what would happen? Well, a lot of those fragments would come our way. So let's speed this up and see that happen. They would cool. Boom, boom, boom. See that? See the Earth getting peppered? Oh yeah, the Earth was getting peppered by fragments. Well, I didn't see too many peppered though, did I? Very, very funny. Gas mask. Oh, yeah, you're right. They should add a nukes for giggles. Yeah, that would be pretty funny. Here's one. Boom. Oh well. That's when the gods get angry. They just say, "And you're gone." Not that one. I meant the red one. Oh, I'm sorry. I was supposed to blow up the red one? Yeah. Speaking of the red one, here it is.
Wow.
Here's Mars and its moons, Phobos and Deimos. Now, what would happen if one of Mars' moons struck Mars? So let's do that. Let's launch and let's find not Mars, but let's find its moons. We should find the moons. Here's Phobos. So now we're going to launch Phobos at Mars and see what happens. I don't know how fast it's going to go. Let's try this. Oh
boy.
Yeah, that's pretty good.
Oh, wow.
Wow. Now, Mars doesn't... Huh?
Not bad.
No, Mars doesn't have much of an atmosphere, so we'll see that much of the impacts will get absorbed. And, of course, these are all the secondary impacts for the local impactor. And then let's try Deimos. Let's see what happens when Deimos hits Mars. Wait, was that Deimos?
Collide,
Wow.
Andromeda and Milky Way.
Ooh. I think we can do that.
I think we can too.
Yeah. Wow, okay. Well, let's just try something else. Let's do this. Let's just go hog wild. Ready?
All right.
Boom, boom, boom. We're launching Deimoses at Mars. Every which way.
Empire Strikes Back.
Yeah, the Empire Strikes Back, all right. And there they go. Wow. How many Deimoses could it handle?
Look at that.
What would you do for a Deimos attack? Now see, there they come, the deadly projectiles. It's like Missile Command, isn't it?
Right?
Wow.
Well, if there was life there isn't.
Right? Well, we got lots of new craters. Look at that. I'm actually liking that. We can actually make these new craters on Mars. I think that's, or anywhere. if you do them too fast, what happens is they hit each other.
Look at that, 4 of them in a row.
I know, right? Not bad. You know, that's so this is Universe Sandbox 2, folks. This is kind of a fun one. If you haven't experimented with it before, the latest one has these new features. For instance, every impact now generates a crater, and it's realistic size and so forth. This is something that it didn't do in the past, so I'm really happy that it's doing it now.
Yeah, and I heard that they're working on Universe Sandbox 3 for a 2022 release.
Ooh, yeah.
Which is going to be crazy because the computing power is getting there. With, commercial computers. So.
Are we going nuts or what? It's like aliens are attacking Mars.
You sadistic son of a...
Hey, now, yes.
It's killed Martian life.
Hey, I wonder if we can destroy Valles Marineris. This is the large canyon on Mars.
You just filled it in.
Yeah, that's what I'm trying to do. See if I can fill it in. That might not be enough. Let's do a few more.
We're going to have to speed up a little bit so we can watch it when it cools.
I know. I got to bring it around. So here we go, folks. We're going to bring it around. Uh-oh. Oh, we heated up Mars.
And they're dead.
They never were alive. Yeah, see, too much kinetic energy being translated into thermal energy.
And let's do some more.
Hey, it's like...
It was red when I got here.
Yeah, that's right. It was all red when I got here. If we do enough of these, well, it'll... Yeah, it'll just end up turning... Oh, look, there it is. Valles Marineris is almost gone. Well, very cool. I mean, Mars has now become a little cinder in our solar system, a solar cinder. What do you want to do now? You want to collide galaxies with each other?
Yes.
Okay, Milky Way and Andromeda collision. Here it comes.
Oh.
Okay, here we are. Now, Andromeda's got perhaps a trillion stars in it. Maybe 2 trillion. Yeah, about 1 trillion stars. And we've got upwards of about 100 billion. First thing you'll notice, just slow it down, you'll see that the dense areas of these galaxies are being attracted to each other this way. This is, incidentally, this is new. I could not do this before.
1 million years per second.
Yeah, well, you have to, because if you go present time, it ain't gonna be much.
Right now, we're 35 million years into the future.
That's right. 38 million years. There's an ejected galaxy core down there.
What do you call them? Mini satellite galaxies?
Yeah, it's ejecting. It's ejecting it. Ejecting these fragments.
And they are kind of staying together.
Yeah. Well, their gravity is doing that. Actually, let's see if we can accelerate this to see what we're gonna get. Okay, because what's happening is it should make. It's showing it vanishing and segregating out, and I don't believe that's gonna happen that way. I think that they haven't got their cosmology, packs in here yet. Because what will happen is the collision between the Milky Way and Andromeda is going to result perhaps in a bigger galaxy that might be an elliptical, a very large elliptical galaxy.
A little circle.
So that's that little nebula that I.
Oh.
That's that little nebula that I. You see, there's a bunch of little nebulae fragments down here. They're all over the place. See all the little circles?
Just go past your camera view, back out a little bit, and see if it becomes more visible.
There's
whole thing as a whole, where Milky Way and Andromeda collided.
Right. Okay, well you can't really.
Yeah.
Yeah, you can't really see.
Wow.
But that's not how. I don't think that's how it would look. I think that they fall short on the galactic stuff, but that's okay.
Supernova in galaxy. What? Yeah.
Oh, what'd you say?
It said the one below this one said supernova in galaxy.
Oh yeah. Well, here's what I like to do. I want to inject another supermassive black hole into the galaxy.
Okay.
Let's do that. So if we go to black holes, let's inject one that is a galaxy, a galaxy-sized black hole.
Oh boy.
All right, here we go. Here we go. We've just injected a new one. We actually have a video that took like 10 years to make, but the video shows Sagittarius A, the central black hole. It shows the stars circling the black hole. Look for that online. It's Sagittarius A time lapse, and you actually watch this happening. It's so amazing. Wow, look at that.
Mm-hmm.
Yeah. Very complex. I think those are the globular clusters orbiting in part.
Dude, it's just absolute chaos.
Galaxies are fairly ordered. And the fact is, to show the Milky Way correctly, they're showing it as a spiral galaxy. And it's not a spiral, it's a barred spiral, meaning our nucleus is extended. Okay, this is not doing anything for me. Let's do supernova and galaxy.
All right.
I think that, if I remember, this wasn't... okay, it's showing a supernova remnant. Now, when a supernova explodes in a galaxy... I have to tell you, the galaxy imagery, this stuff, really, really is superb. It's really impressive. And their supernova remnants are actually pretty impressive. This is different from what it was. This is more true to what we might expect. For those of you who've seen SkyTour LiveStream, where we actually... And it's gone. We're seeing... That's where it's not to what we'd expect. When you see SkyTour LiveStream, we've actually seen supernova remnant, the Veil Nebula. And it's very, very much like that. It actually kind of looked like that. Yeah. Well, anyway... What else you want to destroy?
Well, what else we got?
Well, let's look at a random galaxy collision.
All right.
We now join this collision already in progress. Interesting, because right here, this is an astronomical object that we've actually seen in SkyTour LiveStream. It's called the antenna galaxies, and it shows two little weird antennas and then this stuff in the center. It's actually the result of two spiral galaxies that are in the process of colliding, and this is where they are in our current in our view from SkyTour LiveStream. We're actually seeing it, and from the Earth, we're actually seeing them at this point in their evolution. If we kept watching them over the years, they would end up doing something else. They would end up doing things sort of like this. They would make some strands and some spindles. I suspect they're going to actually come back together and form a large elliptical galaxy like M87, the one that has the black hole that we imaged for the first time 55 million light years away. So showing these vanishing is, I don't think, proper. It's the only little nit I have with Universe Sandbox 2. I don't think that's correct.
Ring of galaxies. That's cool.
Oh yeah, Ring of Galaxies. Now this, of course, isn't real, but this is just fun. Let's watch what they do.
Get close together. Oh yeah.
Oh, we're gonna have one hell of a collision here.
Okay.
Right.
Oh boy.
Oh yeah. Now,
together we can be free.
Now, why are things all getting whipped out? Well, because what happens is, and this is, again, incorrect at this point, what happens is when galaxies collide, they will have some objects and nebulae and other stars and so forth that will end up in these parabolic orbits. They will end up in hyperbolic orbits, meaning that they will pass by each other and whip around each other and then get ejected from the system. But not everything's going to get ejected like it's showing here. So this is not true to form.
Like little clusters everywhere.
Yeah, you're not going. That's not true to form, unfortunately. But it's okay. Here's an elliptical galaxy. These are ones we've seen. This is like we're in M87. So an elliptical galaxy basically has no arms. It sort of looks like a sphere like this.
It's like a hot mess.
Yeah, it is sort of like a hot mess. And boy, you know what can make it even hotter is to inject a black hole that's a supermassive galaxy black hole, like Sagittarius A. Should we do that? Yes,
Sure.
we shall. In fact, let's put in several. Oh my. What's that going to do?
End space and time as we know it? Just a guess.
I think that we're going to have many Sagittarius A's in there. Now, what's that doing?
Making spaghetti.
It's making spaghetti, right? It's like looking at sauce boil. Okay, so...
Well, nothing really.
Nothing really. Oops. We saw something eject there.
Now it's a galaxy plus black holes.
Yeah. Well, you know what? Makes me wonder about something. Let's go back to the very beginning and let's just say empty simulation. Okay. There's an empty simulation. And let me view. We can take the view and make the background okay, that's bright, too bright. I just want to get rid of just stars. Here we go. Okay, this is what I want right here. Now what I'm going to do is I want to go back to our add tool, and I'm going to add a black hole, and I'll make it a Sagittarius A size black hole. Boom. Okay, now I'm going to add another one in orbit around it. Okay.
Oh, are you trying to make gravitational waves?
I am.
Lygos would be proud.
Yeah. Yeah, we got to catch up to one if we're going to be able to see one here. Here we are. So now these are in orbit around each other. The LIGOs, yeah. Interesting thing now, they're orbiting each other, okay, and they're traveling through space. So, you know, from an orbital kinematics point of view, this thing's just got an elliptical orbit around this. But what's really happening? They're actually making these weird paths through space. This is what they actually are doing through space. See that? They're being pulled by each other and making this change. It's so incredible. Now, what would happen if we launched a black hole the size of Sagittarius A at this galaxy?
You mean at the black hole?
Yeah, that's what I mean. At the black hole. Nothing, Beavis.
Right?
Yeah, I don't see anything.
Didn't really seem like it.
Yeah, I know. I'm trying to get colliding black holes here. A little clumsy with this right now. Let me see if I can launch another black hole at Sagittarius A. Let's do that. Just right here. Okay. I said, I wanted to launch. So why is it doing that? It won't let me. For some reason, I hit launch and it's not letting me launch the black hole. It's making it go in orbit.
A message is going to pop in. Sir, do you realize you're trying to end everything as we know it?
You're right. You're not allowed to create death and destruction throughout the universe.
There's one floating way out there.
Yeah, there is.
Might be attracted to this one.
I'll have to come back to this because I was trying to get this to happen, but it's just not working. All right, that's not a problem.
I got an idea.
Yeah.
Go a new empty map.
Okay.
Okay.
Go into an empty map.
Okay, go ahead and give us one of a sun like ours.
Okay, a star like ours. I am trying to find the sun like ours. Where's our sun?
I don't know.
Must have been right at the very beginning. There it is. I forgot. There we are. Okay, here's the sun.
There we go. Now take Mars and put it at 1 Earth unit.
Ah, that's a good idea. Let's try those things. What would that? Well, yeah, it's
Mars where Earth should be.
yeah. Let's try that. It'd be kind of hard. Let's see.
It should just be 1. Let me see what you got here.
I'm trying to read it.
70 million kilometers. Oh no, 702,000 kilometers. How far are we from the sun?
We're 93 million miles.
Oh. Oh, it's because it's on the sun. That's how far across it is. Okay. So that says what? 3.6, or is that what is that? Well, that is hard to read, isn't it?
Yeah. I'm trying to read it here.
366, 166 maybe? Let me see if I can see it on the YouTube. I can't even see it on the YouTube.
Hang on, I'm going to see if I can read that. I mean, what we want is we want it to be basically 150 million kilometers is what we want. So right now, let me see what it says. It says we're at...
It says 3.
Yeah. Yeah, no, we're still order of magnitude too close. We got to get farther away.
All right.
So let me... I wish there was like a... on the screen, like where you can see how far away.
Where you can dim the sun. Okay, there's 1,911,000. Oh no, wait, 1, 2, 3. Yeah.
And we're still too close.
Yep. We're going for 150. There we go. So that's 400 and some thousand.
Yeah, right. We're going to be 149 million kilometers away. So what are we at? Can I read that now? It's
400.
okay. We're in the right neighborhood now. We just have to come back to 149.5. That's where we're kind of going. Oh, too close. I gotta go way to the side to read it.
Yeah.
All right, this is more like it. We're getting better now.
That's in 200.
Yeah, I was almost there. Okay, that's about
right there.
Right about right there.
Yep. Okay.
Okay.
Mars there.
All right. There we go. We got Mars.
Okay, we have Mars orbiting the sun.
Right. Now Mars, surface temperature. Well, keep in mind it doesn't have an atmosphere, so
that's true. Let's see. So
we can give it an atmosphere though.
Let's give it a.
Surface pressure is 6 millibars. Let's increase that to 1,000 millibars, which is Earth.
All right.
All right. So 1,000 millibars.
Oh my God, it's on fire.
Well, look what I did. I moltenified Mars. Why did I do that? Oh, the greenhouse effect. Okay. Shoot. Well, that wasn't fair to Mars, was it?
Well, we can always cool it off.
Yes, we can. Average albedo 0.25. Well, that's part of the problems too. We want to increase the albedo a little bit. I don't know what ours is. I don't know offhand. But if I go to 0.72...
People watching what albedo is?
Reflectivity.
There you go.
Okay, so
it's on fire, just cruising around.
I know, right?
816 degrees Celsius. Climate, let's turn climate on.
I'm trying. It doesn't want to let me.
Maybe because it's too. We got to give it an atmosphere.
The atmosphere. Look, see, we're only at 1 bar right now. So let's go to 100 bar. Let's see if that. See, that's gonna do that again.
Nope.
Greenhouse effect. Okay. See,
Wow.
folks, it's a lot of trouble building a planet. There's a lot of trouble building a planet. A lot of trouble.
Step limit. Wow. So there was probably no way that we could give Mars an atmosphere.
No, we can. We can. Actually, we probably would have been better to terraform Mars farther from the sun, rather than closer, because we're trying to make it into Earth.
Yeah, I just wanted to see what its temperature would be if we just gave it like just a basic atmosphere.
Yeah.
You know, I don't. You can't give it magnetic fields in here, can you?
Yes.
Can you?
Yeah, that's another thing. So let's, for instance, let's go here. Let's go to Mars, and now let's go to composition. See, right now, the composition's not right. We got to add some water to Mars.
Oh, look at that outgassing.
Yeah, it is, because this particular Mars is losing atmosphere. I mean, I'm just playing with this right now, so this is not. I want to increase the iron core though. And now, if we come down here, we want to turn on magnetic field, show magnetosphere. All right, and we don't have any. Magnetic field is 0 right now. Let's make it. Let's make it 10 Gauss.
Okay, we definitely got a different color Mars.
Well, yeah, only because we added some. Yeah, see, there's our magnetosphere.
Look at that.
Yeah, but it's losing mass. Surface temperature is rapidly warming, and we would like to change that.
Well, surface gravity, we would want to give it a little more, right?
Well, we increased the mass, but then it's not Mars anymore.
That's true.
See, Mars now has very, very thick cloud cover. So it's kind of interesting. And it's not streaming, Mars isn't streaming like a comet. Mars is in orbit going this way, but the solar energy is pushing this away. So that's why you're seeing it trail behind it like that, guys. Yeah.
Wow.
Hey, Gas Mask, talking about Subnautica. I've been playing Subnautica for about a year, and yeah, I mean, it's one of those programs or those games where you kind of get sick of it after a while, because it's sort of the same old thing. But it's really cool. I actually, without cheating, I actually built massive sets of stations on the ocean floor on this planet. Gone to the ship that crashed and got all my stuff and so forth. It's kind of cool, So, but I'm kind of tired of Subnautica now.
How about we make our own planet? Let's put a sun and let's make our own planet.
All right, let's try it if we can do that. Don't know if we can.
We'll with input from the people in the chat.
Okay.
We want to make a planet that would support human life, obviously. A planet that we could live on. Now, obviously, there can be some slight fluctuations, like in maybe a little more gravity or a little less gravity. Stuff like that. But it definitely needs to have water. So we need to do how much water, what kind of core it has, and we're going to build our own home and maybe a super Earth at that.
Yeah.
See
You
what
know,
we come up with.
you've heard of Build-A-Bear? Well, this is Build-A-Planet.
Build a home.
Yeah, build a home. There we go. Which
So let's
build a
well,
home
do we
spells
settle
ba.
on, we want to settle on an Earth 2 times the size of this one, but maybe less dense
Can we make that?
to kind of even it out a little bit.
Can we do that?
I think we can. I
We
think
have
there's
to-
a density
well,
scale.
do we have to first start with a planet we know, like Earth? We can't just add generic planet, right?
I think it doesn't have like rocky planet, like unnamed rocky planet.
Well, we can start with one of these exoplanets, sure, but let's see.
I thought when it had just like a generic rocky planet.
Well, let's just get another row going here. Let's just for the time being, we'll just put these up here for now.
All right.
In case you haven't noticed, folks, this is one cool program for $24.99. Okay, I'm telling you. Oh, by the way, I just want to say hi to Shep in chat. How you doing? Lorraine is here. Good to see you, Lorraine. Haven't seen you for a while. 24/7 Live AZ Skies is here. Hey, good to see you too. I want to announce to everybody that SkyTour LiveStream has secured a land loan, not to say money, but a land location in Arizona under a dark sky. That has been done. Yahoo! So SkyTour LiveStream will be moving to Arizona sooner than later now. All I have to do now is work out the finances for the roll-off roof observatory, and we will be ready to move the telescope. I've got people out there already that can work on it with me to help me convert a pre-built shed, a small one, into a roll-off.
Keith has a flatbed that a dome could go on out to Arizona. Wink, wink.
I'm not going to use a dome in Arizona.
Well,
You know why? You know why?
probably.
Because a dome will require a motor to turn the dome around. Don't worry, we're going to get back to this, guys. I promise. A dome would require a motor to spin it around and a motor to open and close the shutter. A roll-off roof observatory, on the other hand, would simply require a motor to roll the roof off the building and back on. And that's it.
Okay.
Yep. And I can use a roll-off roof observatory, and if I get one that's long and thin, a generic building, then what I can do, you see, is I can put more than one pier in there. And with more than one pier, I can have more than one telescope. And then any of you could use a telescope all yourself for a night while I'm taking pictures for SkyTour LiveStream. So in other words, it's going to make another telescope available to people who want to do it. And like maybe a group of people, say you and a bunch of friends might want to say, hey, let's go do some astronomy tonight. Where? Arizona. I don't live in Arizona. Doesn't matter. We can use a telescope out there and get you guys into there. So that's kind of what I'm planning on doing. So, if it gets good, and I can get a building that has enough room for 3 piers, then what I'd like to do is be able to have a 3rd pier so that I can rent that pier to a university that might want to either put their telescope in there or use an existing telescope that we've got and rent a telescope. I think that would be pretty cool. And then they would pay us a monthly fee to rent that telescope to do their research. I got to talk to Cosmic Lettuce as well, because Cosmic lives in Tucson, and I think that he and I might be able to do something together on this. But all cool stuff. Anyway, back to building a planet.
My vote is 69C.
Yeah, Kepler 69c?
I think that would be a good one to start with.
Okay.
And we can adjust its parameters and whatnot. Just make sure the time's not moving so we can adjust everything before we put it in motion.
Okay. That's not it.
Yeah, what is that?
That's 69C.
Sure as hell doesn't look like it.
Well, how do we know what it looks like? Really?
Well, it's the blue one right there.
Yeah, I know.
Wow. Did I say the wrong one, maybe?
No, your 69C is what's showing there.
Oh.
But don't worry. So these are exoplanets. Let's try 62E.
All right.
Ooh, we got a glacial planet here.
Hey, if we warm that baby up, you know what that means.
Yes, and plus it means there's a lot of water there.
Or as people in Philly would say, water.
Yeah, and of course we don't have a star for it to be circling around. So let's first of all, let's put a star in, shall we?
The star. You want to do a binary star system?
I get another. I was thinking something along that line. I'm thinking, let's do Wolf 359. This is a really peculiar red star. Okay, it's much smaller than the sun.
Cool.
I don't know where the habitable zone is, so that's what's going to make this fun. So let's take 62E, and let's see if... I know we can't bring it anywhere near the distance that our Earth is from the star, because that's way too far. So let's try... what's this, 11 million? I can't read that.
It's like 1,223,000.
All right, let's try that.
All right.
Yeah, just over 1 million. Let's see what we got now. Okay, so now that's in orbit around Wolf 359.
Switch that to Fahrenheit.
Yeah, temperature is actually fairly comfortable.
Yeah, it's not too bad. That might warm up as well.
That's actually about the equilibrium temperature on the Earth, I believe. Okay.
Okay.
26.3. There we go.
We're gonna name our planet, people.
Oh yeah. What are we gonna call this, guys?
Let's see. Gotta name it something like now we can do joke names, of course, or we can do something serious that you think, like, say, like me and Mark were talking earlier about how there should be a holiday to celebrate the guy who invented air conditioning. It's on summer solstice.
Should we call this? Let's call this planet Freon 1.
Freon 1. Well, that gives it an indication of like being cold, and we want to make a nice, comfortable planet. But once again, as you said, that might be the median temperature or whatever.
Yeah. So let's just.
So
here's Freon 1. It's a planet. It's ours. We now own it. So.
No, we just call it Freon.
Okay. Well. Okay. Freon.
You don't see none of our planet like Jupiter 1, Jupiter 2. Well, we do have Jupiter 2, but it's
yes,
a ship.
that's true. Here we go. Freon 1. Freon.
There we go. Ladies and gentlemen, welcome to Freon.
Yeah, welcome to Freon. You're here with us. This is Freon. Where's Freon? Freon is this little tiny planet circling one of our nearby stars called Wolf 351. Sorry, Wolf 359. My mistake. And our planet Freon is an exoplanet. It started off life as Kepler 62e, I believe, and it is now made it into. Oh, look, we have we can put in dice and stuff.
Already done.
Yeah.
Okay, so the first thing we need to do is oh, that's 4.5 Earths. We need to take it down to 2.
Okay, we can do that. Let's see what happens. There we are. It has shrunk to 2 Earths in diameter.
Okay.
Density is 5 grams per cubic centimeter. I'm okay with that.
Okay. Surface gravity.
Surface gravity is going to be calculated based on the mass, so that's nothing we can change.
So mass is 2 Earths.
So think about it. The gravitational force is going to be...
down the density, right?
Yes, we could change the density.
So if we lessen the density a little bit...
Let's say 4.
Okay.
Not 4Q, 4. Okay, we don't want the planet to be too puffy, though.
No, don't want it to be too puffy.
Okay. See, now, the radius will vary because the mass and the density could determine, or in part, be partially linked to the radius, so we have to be careful.
Okay.
So calculated radius is off. I'm turning on calculated radius, so it'll calculate the radius based on the mass and so forth, and the material. So composition, Okay, we have some healthy water in here. We have an iron and silicates.
We want a nice molten iron core.
Mm-hmm. We do.
Okay.
Well,
and then,
it's
silicate.
it's solid. I'm gonna bring it down a little bit to a little bit more like the Earth.
There you go.
Okay.
We wanted about 60% water.
Okay, I'm not. It's 100% water. We don't want this. That's the interior, so we want to actually say, okay, let's put it at 62. Just write that for now, and
And hydrogen.
hold on. Can you hold on a sec?
Yeah.
Hold on. Hey, Dave, how are you?
Dude.
I'm all right. Yeah. Yeah, that's starting around midnight our time, yeah? No, I'll do it on Skype. I have a fairly professional radio setup here. So, it'll be good. Do you have my Skype address? Hold on, folks. Yeah, it's a... Okay, it's just mark.d'Antonio. Keys.
I got to keep them entertained.
Well, nothing ever goes right. Folks, I'm talking to Dave Scott from Spaced Out Radio. I don't know if you've heard of Spaced Out Radio. It's a wonderful show to listen to. And tonight, midnight Eastern Time, and 9 o'clock West Coast Time, I'll be joining Dave and going on his show. So listen to Spaced Out Radio tonight, 9 o'clock Pacific, midnight Eastern. I'm actually live on my stream right now, Dave, so I just gave you a little shout out there. Sure I can. All right, let me try that. Keith, just take over for a minute. I'll be just trying to...
Not a problem.
Adding Dave here. Okay. And you're just Spaced Out Radio, right, Dave?
Spaced Out Radio.
Okay.
Me. So there's our planet. Hey, look, I think we're getting clouds on our planet. Look at that. Very, very, like, barely there, but they're there. We're starting to get a little bit. We are, let's see. Oh, I can't see the temperature. That's okay. I wonder why they want us to add hydrogen.
I'm not sure.
Give our little planet a moon, too. But maybe not a tidally locked moon. We'll give it like a real small one, almost like a Deimos-sized moon. That's a little bit closer than ours.
All right, Dave, I'm trying to add you here, and, you know...
Planet canvas. Well, we are going... Okay, so this planet's not in motion at all.
All right.
We're kind of building our planet before we actually put it into motion. See how it reacts.
We know
to
I have an idea. Let me investigate Skype. I'll be ending this stream in a little while, and then I'll talk to you, and I'll get it all straightened out with you. All right, man. I'll talk to you in a bit. All right, bye-bye. Okay, folks. Sorry about that. I had to just take that call because I have that radio show tonight I have to do with Dave. But do tune into that. That's Spaced Out Radio at midnight Eastern, 9 p.m. Pacific.
And don't forget about SkyTour Radio, Sunday nights at 8.
Oh, SkyTour is on Sundays, yeah, 8 to 10. No.
Okay.
What are we doing here?
Why would we add hydrogen? Explain.
Hydrogen, of course, is very important for water.
Right.
Yeah, but we have
hydrogen.
Yeah, so let's add a little bit of hydrogen. See, you had too much right away. Look what happens.
Yeah.
You know, we ended up with a gas giant, and that's why you would add hydrogen to make a Jupiter. See, and we don't want to do that.
Do we need a very, very, very little bit of hydrogen or no?
No, I don't think we need any because we have a very tiny amount in our crust and so forth, and a little trace in our atmosphere, but not much. Okay, so surface temperature is actually not bad.
It's not bad.
It's holding. It's holding, which is good.
What is mass loss?
If a planet is being heated by the star, for instance, it could lose some mass of its atmosphere to solar interactions. Mars, for instance, ultraviolet light would take H2O in the atmosphere, split it apart. Hydrogen gets lost to space. That's mass loss. And the oxygen, gets bound up in the crust, making it red, iron oxide, Fe2O3.
Right.
So we don't have any mass loss, which is good.
Well, let's go to motion because we want to put this thing spinning a little bit. That way, we're not getting direct sunlight on one side the whole time. So, let's see. Now it's twice the size of Earth.
Yeah.
So.
Well, we could say it has an orbital period of 21 hours. I mean. Let's hang on a minute.
Orbital parent.
Okay.
Okay.
Look, see what I did?
Go. Look at Freon.
Well, I actually put it into motion. See what we got?
Mm-hmm.
All right. So now with it in motion, you can actually see that we have water, we have oceans.
Yep. We have liquid water.
That's right.
So
we were successful in making our plan. Now we have to look at what's happening with our magnetosphere. Show magnetosphere.
It's 49.9% similar to Earth.
Right, but we don't have a magnetic field.
And it's dropping quick, the life likelihood.
Right.
It's dropping.
I stopped it now.
Okay. So we definitely need this stuff. Magnetic fields.
Yeah, magnetic field is what protects us.
Yep. So let's go ahead and give it all a magnetosphere and the magnetic field.
Yep, I will. That's a good idea.
So I think that's why our life likelihood was dropping so quick.
Yeah, and we have to just
and then we'll give it a moon then once we get the planet stable.
Well, I mean, we're playing gods.
Yep.
All right, let me Okay, our planet should have a magnetic field of around 0.65 Gauss.
Okay.
Okay.
Yep.
All right, and there is our magnetic field. You notice there's no outgassing. Wait, I don't know that yet. I gotta put us into motion. Okay, we're in motion. Okay, so now that we're in motion, you can see that we have this stable magnetic field.
But we're still dropping.
What are we dropping? Life likelihood. Oh yeah, okay. Well, that's probably because of the atmosphere. We need an atmosphere.
Yep. We need a. You did a magnetosphere. Okay.
Yeah.
All right. So let's do that.
Atmosphere. Surface pressure is 35 kilopascals, 192 atmospheres. What about
Yeah, let's do an Earth.
Earth atmosphere? Yes.
There we go.
0.9. That's not bad. That's actually pretty good. You could live in 0.5.
Surface pressure.
Yeah, if you want to do that in a more reasonable one, you can see it in atmospheres. It's 0.351. And I think that's calculated. Greenhouse effect 60.7 Celsius. Minus 350. That wasn't right. This must have said minus 60 points. Greenhouse effect minus 60.7 Celsius. I'm not sure what this parameter means because in Fahrenheit it says minus 350 Fahrenheit. I don't get why it's doing that. Oh, infrared
scale height too is another one.
What's that? Oh, atmosphere scale
scale
height.
height.
Yeah, I believe that's a calculated value.
Oh, it's calculated based on that.
Yeah. Yeah.
Infrared
emissivity. Yeah, that's how much of the thermal energy comes off of it, basically. How much heat it'll show. Show atmospheres on. Show clouds on. What are we looking at here? The water's gone.
What's it doing?
The water's gone.
Okay.
Yeah.
So we have ice now. Yeah.
We actually don't have much now. Jeez. Let's just launch something at it.
We're so close.
No, we're really not.
What's actions? What's under that tab? Oh, so that's how you save the object.
Yeah, I see it now, yeah.
Rotation lock. Okay, so that's all the options for the thing. Well, we almost had it. We had water for good 6 days.
A little while, yeah. That's right. But we get, the bottom line is we could certainly work out all of these things. Not a worry. We'll shut off the magnetosphere because you don't need to see a magnetosphere when you're launching Deimos into it.
Not Deimos. Let's launch something big into it. Let's launch Earth into it. It's twice its size.
No, I just want to see what happens when we launch something like this into it. Okay, let's slow it down. Now let's go here. Deimos. Where the hell is Deimos? I was launching it. I want to launch Deimos. Why is it orbiting? I didn't want it to orbit. I wanted it to launch. I hit launch. See, I put it on launch. Why would it not let me launch?
Space and time.
Okay. Does this look like a? This looks like orbit. This doesn't look like launch. And I'm saying launch. Okay, you know what? I'm gonna do this again. Launch. The moon. Now it's gonna launch. Oh my.
Oh my.
Well, that's what you get, planet.
It was good knowing you for 7.5 days.
Yeah, for 7 days, and now it's leaking. Exactly. Oh my.
And all our water that we had.
Yeah. Oh, I had a gas mask. I had space engineers too. It was kind of funny. The first variations of space engineers was kind of clunky. Kind of reminded you of far better than Minecraft, but it was sort of like Minecraft in space because everything was based on cubic constructs and putting things together like that. Yeah, but it was fun for a while. Space Engineers has actually come a long way as well, and so that's kind of cool. But let's be honest, Universe Sandbox. I mean, look at Look at we're in the world. Oh, look what we're doing.
Yep.
Oh, look what we've done. Well, see, Wolf 359. Here's another thing too. Wolf 359 is a flare star. As an M-class star, it actually. Oops! I just launched something at it.
You launched the moon at it.
I did. It'll just get absorbed. It's a flare star, so you saw the flares that were coming off. That's actually fairly common with these M stars. You know. Oh, D. Smith, you know, I don't know if giving it a moon made a difference or would make a difference. The moon for us didn't really. If anything, the moon helped objects be attracted to us to impact us more. So the moon was no protector of ours, so to speak.
Well, it helped attract some meteorites that brought water.
Mm-hmm. Well, well, there's that thing too, and I got to be fair about it. It's very possible that you could end up getting the moon attracting more asteroids that head water to our planet. So in that regard, it was helpful. But in that regard, saying that it was actually a necessary for us to be here, I'm not really sure it was. At this point, our planet is down here. Freon is down here on the lower right.
What moon is that?
That's Freon. That's our moon. Our planet we made, and we collided something with it, and all these little fragments are flying around. See, and there's a flare.
Moon.
Huh?
Oh, the Earth moon. Okay.
Oh, yeah, that's an Earth moon. Yeah, that's the Earth moon finally making its way to hit go underneath. Actually, it's gonna go in an orbit.
Well, I'll tell you what. Since we've been at it for about 2 hours. You want to go out with a bang and just show people the Saturn-Jupiter collision?
Sure, let's do it.
Yeah. And we shall make the new planet known as Stupiter.
Is there actually one of those? Is there actually one of those, or we actually have to make the collision?
I think you just got to have Jupiter and then throw Saturn into it or something.
Maybe.
Or was it Saturn and then we threw Jupiter into it?
You know what? Let's just do it. Let's go to our planets and let's take Jupiter and its moons.
Giggity.
Okay.
Mm-hmm.
And there's Jupiter and its moons. Okay.
Get rid of the orbits.
Yeah.
There we go.
Right. There's Jupiter. Now let's see if the red spot is accurately shown.
I don't see it. There it is.
Yeah, look, it's accurately shown.
Yep.
They actually show this is right up to date. I'm very impressed. Because the red spot shows the characteristic fading that it's been doing, and it's leaking down this band. It's pretty cool. Wow. Okay, so there's Jupiter, and now you want to launch Saturn at this?
Yeah, let's back up a little bit and on Saturn.
Alrighty, that's what we're going to do. We are going to launch. Ladies and gentlemen, prepare for the launch of the new corporate entity called Stupiter.
Stupiter.
Mm-hmm. And let me get Saturn here.
Got to make sure its rings are on.
Yeah, you know what? That's one of the problems. You gotta grab it, and then you gotta. What the heck? Oh, I just put. Yes, exactly.
Well, that worked.
Well, not really.
Jupiters.
Yeah, I made a mistake there. I had to. Let's see if I can do this though. If I can really quickly.
What?
What?
What are they doing? Oh no, it's on its own little path. It's not going to go near Jupiter.
Well, it will. I mean, we just have to launch it. That's all.
Yeah, it looks like it's going to fly out.
We can add the ring. Where's the actions? Here are the actions, right? And you say, where's adding rings?
Yeah, I remember it's
Here
in
it
there
is.
somewhere. I just don't know
Let's
where.
add moons. Oh, do we have to actually make the rings?
No, I don't think so.
All right, you know what we're going to do? Let's make it
Saturn.
easier. Let's actually bring up Saturn.
There you go.
All right,
Throw
and
Jupiter.
then we'll throw Jupiter. Yeah. Saturn. There it is. Okay. Now, just so you guys know, the way that Universe Sandbox 2 generates rings is by approximating the rings with objects. Okay? So that's why it looks the way it does. But I want you to see, and so does Keith, how cool it is when a larger object comes in and disrupts it.
Yeah, and back Jupiter off a little bit just so you can see the gravitational effects it starts having.
Yeah.
Before it even actually gets to it. I got to even back it up further than that.
Okay.
I mean, it's a big planet.
And we'll have it come down from the top.
All right.
All right.
I still think that's close.
You do?
Mm-hmm.
Well, it's
just a little bit more, just a tad.
Okay.
Bit. There we go.
And we're launched. And
right,
this is why. This is why.
We need to.
Huh?
I said then we can speed it up if we need to.
Yes, and we will need to.
But check this out. Now you should go for the view from the other side of Saturn, so you can start seeing the effects on the rings.
Well, the effects should be immediate, right? Even now. All right. So let's do that. We should start seeing that.
Here it comes.
Yeah, it's a big one.
That's a big one.
Okay, and let's
speed her up a little bit.
Yeah, well, first let's back out a little bit, and
here she comes. All right. Getting closer. Well, nothing too bad right now.
But it should be though. I'm not sure that Jupiter is on the right trajectory. I don't know. It looks it though.
Yeah, they're pulling a little bit.
See, the thing is, these are really close to Saturn. So once Jupiter gets closer, its gravity is going to really disrupt these rings, and it should have done so by now. Oh, there we go. There we go.
Yep.
Saturn's rings are getting disrupted.
Boing.
Oh my. Oh, that's a deadly shadow. Goodbye.
And now, ladies and gentlemen, welcome to Stupider. Magically whisked away to
Jupiter. It's Schupern or
let's find out if
Jupiter.
Because you know there's going to be a massive gravity bump right there, so it's got stuff around it, you would think.
Let's increase some speed and see what happens.
Looks like the rings are just flying off into space. All the moons are just out, like the police just showed up.
There go the moons. There's the tracks for the moons. Whee! There goes Enceladus. No! Okay, Jupiter is now stupider, and the rings are now all disheveled.
It's just complete chaos.
Total chaos. Yeah, there we go. And it's expanding chaos.
Yep.
And it's expanding chaotically into the universe.
Let's speed her up and see where she goes.
Alrighty. And we'll leave the tracks on.
Yep. There we go.
Oh, yeah.
Sheesh. Look at that. It's just moons are going every which direction.
There's Titan.
Yeah.
Little Titan's going, hey, what happened?
So Titan's still in the picture.
And Rhea's saying, I don't know, but I'm going with them.
The Galilean moons, they had to, go flying.
Yeah. Well, there's Enceladus, there's Tethys. Oh, you know what? The Jupiter, we didn't have any of the Jupiter. We didn't have the Jovian moons.
No.
No, we didn't have the moons.
Look at that. And that's all branching out from collision point.
That's right. Now, this rings. This is only because of this, because of the gravitational effects of the Jupiter-Saturn merge. All right. So if we realistically had Uranus and Neptune and Pluto and Mars in the solar system, then this might look a little different. We're not going too fast to make it all get screwed up, but it's pretty cool. And we're going as fast as we can go right now.
Just stick Neptune like right into the line of that big cluster coming at him.
Like right here?
Like right in front of it, yeah.
All right, let's try that.
Tracks. You're not launching it, are you?
That was a launch.
Oh, you launched Neptune?
It did. Boy, it launched as well.
Just place Neptune there and see what it attracts.
Yeah, I don't know if I can do that.
I thought you could. Maybe you can't.
Oh, wait, maybe that's what this is. Oh, the whole system. Oh yeah, see, now you can launch launch all the moons at the same time. That's cool.
Well, why didn't we do that?
I don't know. I didn't want to actually launch it all with any kind of velocity. I just wanted to set it still.
No, I mean Jupiter and Saturn.
Yeah, I don't know. Okay, well.
There we go.
But now we're going to see what happens at Neptunia.
Neptune, you can't even see.
That's not true.
Well, I mean, on the map, you can barely. I mean,
we'll get it. There we go.
Oh, maybe, yeah, I mean, you just pull it out far, that's all.
Here's Neptunio. Neptunia.
And you said we're going to maximum speed right now.
Yeah, well, not yet. No, I slowed way down.
Okay. So let's see what happens. Let's see if Jupiter becomes a moon of Neptune.
Well, okay, I'm going as fast as the simulation will allow me right now. Here's a little faster. What is that orbiting? Why is it saying it's like in an orbit? It's not in an orbit. Okay, it's its motion. Whoa, hello.
Whoa.
Sorry.
It's rocking.
Yeah.
Well, it looks like some might be headed for it.
I don't know.
Have to wait till it gets a little closer. Yeah, Lorraine. Planetary mosh pit.
That's right. Wow. Well, you know what? This has been a lot of fun.
Gravity's amazing.
It is. Gravity's fun. A lot of fun.
The last one of the night. Just bash 2 Jupiters together and then we'll call it quits.
Oh, all right. We're going to bash 2 Jupiters together. Actually, if we're going to do that, let's do it right. Okay, let's go to our solar system. Just our straight solar system. Go out to Jupiter. All right. And I'm going to pause it right now, first of all. And I want to go out to Jupiter. Where's my Jupiter? There it is. Okay, now we're going to zoom in on the Jupe. And the first thing we're going to do is go out into Jupiter's actions here and add moons. Add moons to the planet. There they are. All right, and we'll turn on the trails. Okay, and we're going to slow it down a little bit. There we are. That's pretty good. Just for now. And then, that's the actual pattern, a corkscrew. And people have trouble understanding that intellectually, but the fact is, this is the center around which the moons are circulating. And just because this is moving doesn't mean that these are going to orbit any differently. They still do that. They still orbit just like they always have. Okay? And because it's moving, people say, you can't move in a corkscrew. That doesn't work. Yes, it does. And it's just that they just can't, some people can't see it. But anyway, enough of that. Let's have some fun with this. Let's go into our tools. And you want to launch another Jupiter?
Mm-hmm. With its moons.
With its moons. Oh.
Yep.
Then I know how to do that now because we can do full system.
Right.
Yes, that's exactly right. Roger that.
So
Mm-hmm.
there's of each moon, and
There
we'll
it
see
is.
which way they go.
Okay, and now we're going to launch. Well, let's launch. Oh, I got to do it this way. Did I say launch?
Sure. Yeah.
There it is. All right. Are you ready?
I'm ready.
Okay, let's just launch them kind of off sides. Here we go. Yeah,
Launch.
that's good.
Here we go.
Planetary mosh.
Oh, it's already.
Oh, it's already starting to wreak some havoc. Oh, let's get closer, shall we? Oh my.
Well, the two Jupiters are vying and jockeying for position.
Yeah, no more jockeying. Look at this Io. God. Oh, wow.
Oh, the humanity.
Oh, the humanity. Wow.
Yeah.
Whoa, I don't believe that. I know, huh?
Look, that we just lost. What is that?
All these planets up there, and then Europa is sailing. Says, "I'm out of here."
Europa's heading to Andromeda.
Europa's like, "I'm out of here. I'm done. Thank you."
At the size of that new hot red lollipop.
It's like, thank you very much. I'm out of here.
Did any moon stay around Jupiter?
It looks like the impact pretty much drove everything away, at least momentarily. Because
Io was heading to Ganymede's heading out.
let's speed it up.
The two Ios are twinning up. That's cool.
Here we go.
Europas are kind of twinning up.
Look, it looks like Ganymede. Naki's coming back.
Oh, we almost had another collision.
Oh.
Look, Europa's down there somewhere.
Yeah, Europa has the other Europa. Metis looks like it's sticking around.
Close. No, just missed one another.
Wow.
That is just a mess. But yet its gravity is still holding it in somehow, like holding them all around it.
Well, it's the strongest gravity well in the solar system besides the sun.
I mean, look at that.
Yeah. Let's see if it settles down.
Mess. And they're all still following along.
I'm going to turn off the tracks. Just to...
The way Ganymede is actually the new Rudolph. It's leading the way out.
Well, let's drop it down now and see who's... We do have something that's settled into a stable orbit. See this? And it's Metis.
Look at that impact on the Jupiter.
Yeah.
It's crazy.
Metis has made a stable... yeah, look at the impact right there. The impact scar.
That damn red spot. It's still there.
Well, again... They haven't thought about that far. So out of all the moons that Jupiter has, 68 or 69 moons, only one has stuck around, and that's Metis. And I don't even... Is Metis Saturn's moon or Jupiter's? I don't even remember.
It's Saturn's, but...
Is it?
No, it has to be, because we combined two...
no, we had two Jupiters combined. Oh, you're right. It's all Jupiter. So we had two Jupiters. I thought we collided with Saturn.
At Europa, I'm not sure if it's heading out or if it's trying to stay with Papa Jupiter. It looks like far out there.
Let's find out.
No,
hyperbolic orbit. Look at this. They're all like, "Hey, where'd you go?"
Oh, look at all that.
Hey, where'd you go?
At least they're just sitting in the middle of two giant, moon fields.
Here's another Europa.
Yeah.
Jupiter's pretty powerful though, so I think that it's gonna over time it's gonna hold something. So let's just zip this around and see what we get.
All right.
Just a little longer.
The dust. Ganymede, just put it away, I think.
Europa's still... Yeah, no, it doesn't matter. See, it looks like it's... Europa had enough energy. Europa 1, I should say, had enough energy to zip away. Ganymede, also going away, had enough energy. So I just think it's odd that if two Jupiters collided with all their moons, the way we did it anyway, we found that we would only have Metis be the only planet, or moon rather, that would stick around Jupiter. That's pretty cool.
And now made a stable orbit.
And it made a stable orbit, yeah. In fact, it did make a stable orbit. Its orbit's actually quite stable, which is amazing. It's a very well-refined orbit. Wow. Well, folks, I want to thank you guys for joining us on this fun little foray into Universe Sandbox.
We do this once in a while.
Yeah, once in a while. I want to just say hello to Lorraine. I hadn't said hi to you officially before tonight. Tim F., welcome, and glad you joined us over here. Sorry about the snafu over on P and K. But to all of you, Shep, I didn't talk to you yet. I'm glad you got here. Put AC, nice to see you. Welcome, and hope you had some fun. Normally we do the things with the telescope and the observatory. And last thing I want to mention is that I did secure a land location in Arizona for the telescope. And I'm not moving it anytime soon. You know, in other words, I'm hoping that there won't be that much downtime when I actually do the move. So we'll see.
Yeah. Do you know when you're having any free time up to do another telescope stream?
Oh, I actually almost did it last night, but it clouded up on me, and the night before, and it clouded up then too.
Yeah, weather's just been crazy.
Well, I mean, I have the telescope here is ready to go, and nothing's changed. I haven't taken anything apart. It's all set. I just cannot wait to get this telescope under the dark sky, so I have to really, really be careful, because I could really jump the gun if I wanted to. There's a lot to do. I have to write the circuit for my little microprocessor that will take the roof on and off the observatory. I've got to get another camera that I can use as an all-sky camera that will let me look at the sky conditions before opening the observatory. Kind of important. And I got to get a weather system that will allow me to look at current conditions and get weather reports for the exact location. That's, you measure all those things in the hundreds of dollars, so trust me, it's not cheap.
It might be nice to get like a little RX station,
yeah.
Station, out there, just the one that gives you pressure, and so you can tell when the pressure's dropping, if there's going to be weather, stuff like that. Just a little station you can mount to the top, or on a pole somewhere.
Yeah, no, they have those. Yeah, you're right. Lorraine, thank you. I'm glad you enjoyed watching the planet smashing. We do this when it's cloudy sometimes, and and if any of you are up to it tonight, starting at midnight Eastern time, I'll be on the Spaced Out Radio show.
1 hour.
That's actually 1 hour from now, yeah. And that'll be 2.5 hours.
And thanks for having me on.
Oh, Keith, it was a great time.
Sandbox once again. He will be on the P&K stream probably soon.
Well, I was supposed to be on a couple times already, and things happened at your end, at my end, and we just didn't. We didn't work it out. We didn't work it out. I mean, this is what this is. This is a ballet. Look at this.
Yeah.
It's a cosmic ballet amid the chaos of collision. Look at this. Here it is. This is the once and previous Jupiters, and look at this. Those
moons will stay.
They've been left behind
for millions of years.
Isn't that amazing?
And people will wonder, why are all these things together? Then they won't know what caused it, generations, millions of years from now.
Once in future Jupiter. Number one. Together. Get us out of here, number one.
Number one, take a number two. All right.
Very good.
That'll for us then, huh?
Yeah. Kind of cool, huh?
Yeah.
We could always take Proxima Centauri and launch it. Oh, did I just do that? Oh, there goes Jupiter. Gets absorbed. Huh? What'd you say?
I said, take it easy, Thanos.
Wait a minute. 2 Proximas. Guess what that does?
Oh, boy. Just destroyed everybody.
It's a
Time and
supernova.
space.
Supernova.
Yep. And dead.
Yeah, supernova.
There you go.
Yeah, now see, this is it says supernova, but actually what this is hydrogen gas, and it has a certain mass. This mass is 258 Jupiters. This one is a little more. Okay, so basically what you can do is you can now throw masses of hydrogen at a spot in space, and it will gravitationally accrete, and you can actually build a star.
I always hang on for dear life.
Huh? Oh, yeah. I was going, get me out of here, never come back. All right, guys, on this note, with the supernova and so forth, I just want to say thank you for watching SkyTour LiveStream with Keith and I tonight. We had a good time, and I hope you had a good time watching our Planet Blasters. Planet Blasters, Inc. You know, that's what we should be called from now on.
And hopefully you'll learn a thing or two. Some little facts thrown in there from our God playing.
Absolutely.
Yeah.
All right. Well, guys, thank you very much. And we're going to talk to you, I guess, next clear night. All right? So we'll see you later. And remember, keep looking up. I always say that. And if Amanda was here, she'd say, except while driving.
Except while driving.
That's it. So we'll talk to you later, guys. Good night.
Peace out.